Hello there, and welcome to Life Beyond Seen, a quiet place where curiosity slows down, the noise of the day fades a little, and science is allowed to speak in a softer voice. This is a space for wondering without rushing, for learning without needing to hold on too tightly, and for letting questions drift in the background while your thoughts settle. Tonight, we're heading somewhere very far from the surface, far from light, far from anything familiar, to a place that exists right here on Earth and yet still manages to feel almost unreal. There is a point on our planet that sits deeper than Mount Everest is tall, a place so far down that distance stops being intuitive and numbers stop being comforting, a place where pressure replaces gravity as the dominant force, where darkness is not an absence but a permanent condition, and where the idea of the bottom becomes surprisingly difficult to define. This place is known as Challenger Deep, the deepest known point in Earth's oceans, tucked inside the Mariana Trench, and despite decades of exploration, advanced technology, and careful study, it continues to unsettle the people who dedicate their lives to understanding it. What makes this especially strange is that Challenger Deep isn't distant in the way space is distant. It isn't light years away or separated from us by time. It's beneath the same oceans that carry ships, shape weather, and lap quietly at coastlines every day. And yet, for scientists, engineers, and explorers, it might as well be another world. A world that resists observation, challenges assumptions, and regularly reminds us how thin the margin is between curiosity and vulnerability. There's something quietly uncomfortable about places we know exist but cannot easily reach. The deepest parts of the ocean fall into that category. Unlike mountains, which invite ascent, or deserts, which stretch openly across maps, the deep sea hides itself. It doesn't offer landmarks or horizons. It doesn't give feedback in familiar ways. Instead, it presses back. Hard. Challenger. Deep in particular is not just deep in a numerical sense. It is deep in ways that affect materials, electronics, human physiology, and even scientific expectations. And that is part of why it still terrifies scientists. Not because it is dramatic or loud, but because it is unforgiving, persistent, and largely indifferent to our presence. As you listen, you might notice how your own sense of scale begins to shift. Depth has a way of doing that. 10 meters underwater feels manageable. 100 meters feels serious. 1,000 meters already feels distant and heavy. But Challenger Deep drops to nearly 11,000 meters. At that depth, water behaves differently. Pressure becomes the defining rule. Everything that exists there must obey it or be destroyed by it. There is no adjustment period, no second chances. And yet scientists keep going back. They go back with reinforced submersibles, unmanned probes, cables that stretch longer than city streets, and sensors designed to survive forces that would instantly crush almost anything else. They go back knowing that every descent carries risk, that equipment failure is common, that data is often incomplete, and that the environment below does not tolerate mistakes. They go back because Challenger Deep holds answers to questions that can't be answered anywhere else. Questions about life, questions about geology, questions about the limits of materials, questions about how Earth works when stripped of sunlight, warmth, and surface stability. But before we move further into that descent, it's worth pausing just briefly where you are now. Where are you listening from tonight? Is it late, or early, or somewhere in between? Are you winding down, or simply drifting? It's a small question, but a fitting one. Challenger Deep exists in a world without clocks, without day or night, without the rhythms we rely on to organize our lives. Down there, time is measured differently, not by hours or minutes, but by pressure changes, sediment movement, and the slow passage of geological forces that operate on scales far beyond human attention. If you find this kind of quiet exploration soothing, or if letting your thoughts wander into places most people never think about helps you relax, then liking the video or subscribing is always appreciated. It helps this small, calm corner reach others who might need something steady to listen to as the day fades out. Now, let's begin moving downward. Not all at once. There's no rush here. The ocean, at first, behaves the way we expect. Waves, currents, light dancing through the upper layers. This is the part we know. This is the part where life is visible, where movement is constant, where sound travels easily, and the surface remains close enough to feel reassuring. But depth accumulates quickly. Within minutes of descent, colours disappear. Reds fade first, then oranges, then yellows. Eventually even blue gives up. Light becomes scattered, then weak, then irrelevant. Challenger Deep begins far below this transition, long after the ocean has stopped feeling like water and started behaving more like weight. What makes this place particularly unsettling to scientists is not just how deep it is, but how poorly it fits into the stories we like to tell ourselves about exploration. We're comfortable with progress narratives. We like to believe that with better tools, better models, and better funding, unknown places become known. Challenger Deep resists that. Every new mission answers a few questions and raises several more. Data comes back incomplete. Images are grainy. Sensors record anomalies that don't immediately make sense. Sometimes, equipment simply vanishes. Pressure at the bottom of the trench reaches over 1,000 times what we experience at sea level. Steel bends, glass shatters, seals fail in ways that are difficult to predict. Even titanium, chosen specifically for its strength, has limits. And unlike space, where pressure differences push outward, the deep ocean pushes in from every direction at once. There is no orientation where stress is relieved. For humans, this environment is instantly lethal without protection. Not gradually dangerous, not uncomfortable, immediately destructive. That knowledge sits quietly behind every mission briefing, every design decision, every descent. Scientists may not talk about fear often, but respect is unavoidable. And then there's the isolation. Signals travel slowly through water. Communication becomes delayed, distorted, or impossible. Submersibles disappear into darkness with no visual reference points. Once they pass a certain depth, there is nothing to see except what they bring with them. Light must be created artificially. Sound becomes the primary sense, and even then, it behaves strangely under such extreme pressure. This is where Challenger Deep stops being just a location and starts becoming a problem to solve. A problem that sits at the intersection of physics, engineering, biology, and geology. A problem that refuses to stay neatly categorized. And beneath all of that, there is a quieter discomfort. The realization that Earth, the planet we live on and depend on, contains regions we still barely understand. That there are processes happening beneath us that influence earthquakes, ocean chemistry, and even climate, all without our direct awareness. Challenger Deep is not isolated from the rest of the world. It is connected to it through tectonic movement, sediment flow, and the slow recycling of Earth's crust. Understanding it isn't optional, it's necessary, but necessity doesn't make it less intimidating. As we continue, we'll move closer to the trench itself, to its location, its shape, and the way it was discovered, to the early assumptions scientists made, and how many of those assumptions failed. We'll look at what happens to machines sent into that darkness, what comes back altered, and what doesn't come back at all. And through all of it, the same question keeps resurfacing in quiet ways. Why does this place, more than any other on Earth, still unsettle the people who know the most about it? That question doesn't have a single answer. It unfolds slowly, layer by layer, much like the descent itself, and we've only just begun. What makes the deepest place on Earth unsettling isn't just how far down it is. Depth alone is something we can put a number on, something we can compare, something we can slowly get used to. What refuses to feel ordinary about this place is how completely it breaks our everyday sense of the planet we live on. We grow up learning that Earth has a surface, an atmosphere, oceans that seem vast but familiar, and a solid ground beneath it all. The existence of Challenger Deep quietly challenges that picture. It reminds us that the surface world we occupy is a thin skin stretched over environments that operate by entirely different rules. Challenger Deep sits inside the Mariana Trench, a long curved scar in the western Pacific Ocean that marks a boundary between tectonic plates. On a map, it looks narrow and unassuming, just another line in a sea filled with lines. But maps flatten reality. They remove scale, pressure, and consequence. In reality, Challenger Deep drops nearly 11 kilometers below sea level, a vertical distance so extreme that if you placed Mount Everest at the bottom of it, the mountain's peak would still not break the surface. That comparison gets repeated often, not because it explains the depth particularly well, but because it is one of the few mental anchors we have that comes close. Even then, the comparison fails in important ways. Everest is visible. It can be photographed from a distance. People can stand on its slopes and feel its presence directly. Challenger Deep offers no such reassurance. It cannot be seen from above. It gives no visual hint of its scale. The ocean surface above it looks no different from any other stretch of water. Ships pass overhead without noticing anything unusual. Waves behave the same. Clouds reflect the same light. Nothing about the surface announces that below lies the most extreme environment our planet has to offer. This disconnect between appearance and reality is one of the reasons scientists find the place so difficult to fully internalize. It doesn't advertise itself. It doesn't feel earned by effort or ascent. You don't climb toward it. You descend away from everything familiar, passing layer after layer where conditions shift gradually and then abruptly, until eventually the word ocean stops meaning what we think it means. At shallow depths, water still behaves like water as we know it. Fish swim, light scatters, currents move predictably. But as depth increases, pressure begins to assert itself in subtle ways at first. Gas compresses, materials flex, sounds travel differently. By the time you reach a few thousand meters, pressure is no longer a background condition. It becomes dominant. Every square centimetre of surface is bearing weight. At Challenger Deep, that pressure exceeds 1,000 atmospheres. It is not something that can be countered by strength alone. It requires careful design, perfect sealing, and an acceptance that failure will be immediate and catastrophic. This is where the place stops feeling like part of Earth and starts feeling like a test environment for physics itself. Scientists are used to extreme numbers. They work with vast distances, tiny particles, enormous energies. But those extremes are often abstract. Challenger Deep is not abstract. It exists physically, tangibly, and it interacts violently with anything that enters it unprepared. When researchers design instruments for this depth, they are not just collecting data. They are negotiating with forces that will exploit the smallest oversight. A flawed weld, a microscopic crack, a miscalculated tolerance. Any of these can turn a descent into debris. What also refuses to feel ordinary is how little time humans have spent there. Despite being part of our own planet, Challenger Deep has been visited fewer times than the Moon. That comparison is not rhetorical. It is literal. The number of crewed descents can be counted on one hand. Uncrewed missions add more attempts, but even those are rare, expensive, and risky. Each descent is treated as a significant event. Each recovery is met with relief. This imbalance creates a strange psychological tension. We are accustomed to thinking of Earth as explored, categorized, and mapped. The idea that the most extreme environment on the planet remains largely unobserved disrupts that narrative. It suggests that exploration did not end with satellites or space probes. It simply shifted direction, downward instead of outward. Another reason Challenger Deep feels different is that it exists in a part of the ocean known as the Hadal zone. named after Hades, the Greek underworld. The name is not accidental. This zone begins around 6,000 meters deep and extends to the deepest trenches. Conditions here are not just hostile to humans, they are hostile to many assumptions about life itself. Temperatures hover near freezing, pressure crushes most known biological structures, food is scarce, sunlight is completely absent. For a long time, scientists assumed that little or no life could survive under such conditions. That assumption has proven to be incorrect, but the correction has only deepened the sense of unease. Life does exist there, but it exists on terms that are difficult to reconcile with surface biology. Cells are structured differently. Membranes behave differently. Metabolism operates at a pace and chemistry that feels unfamiliar. The existence of life in Challenger Deep does not make the place feel more welcoming. It makes it feel more alien. There is also the matter of motion. The seafloor at the bottom of the trench is not stable in the way we imagine ground to be. It is part of an active tectonic boundary where one plate slides beneath another. This process, called subduction, drives earthquakes, volcanic activity, and the slow recycling of Earth's crust. Challenger Deep is not a quiet pit where sediments gently accumulate. It is a dynamic system shaped by stress, collapse, and sudden shifts. Submarine landslides occur here, sometimes triggered by distant earthquakes. Sediment flows reshape the bottom. Chemical gradients change as fluids seep from below the crust. For scientists, this means that the environment they measure is not fixed. A reading taken today may not reflect conditions tomorrow. Instruments left behind may be buried, moved, or damaged without warning. This instability adds another layer of unpredictability. Even if technology survives the pressure, the environment itself may interfere. There is something psychologically disorienting about studying a place where so many variables are beyond control. In most laboratories, conditions are isolated and repeatable. Even in space exploration, trajectories and environments can be modelled with precision. Challenger Deep resists that level of certainty. Models exist, but they are constantly being revised. Predictions are cautious, confidence is provisional. The place also carries a quiet symbolic weight. Depth has always been associated with danger, secrecy, and the unknown. Long before science had the tools to measure trenches, humans told stories about what lived below the surface. Sea monsters, abyssal realms, endless darkness. Modern science has replaced myth with measurement, but it has not erased the emotional response entirely. Challenger Deep sits at the intersection of rational inquiry and instinctive discomfort. Scientists are trained to separate feeling from data, but they are still human. When a submersible begins its descent, when communication delays stretch longer, when instruments pass depths no human body can tolerate, there is an awareness that this is not a routine environment. It is not forgiving. It does not allow improvisation. Even language struggles here. Words like deep, dark, and cold lose precision. They become inadequate shorthand for conditions that exceed normal experience by orders of magnitude. Pressure is not just high, it is constant, crushing, and omnidirectional. Darkness is not just an absence of light, it is permanent, total, and absolute. Cold is not bracing, it is stabilizing, unchanging, and indifferent. Challenger Deep also refuses to feel ordinary because it does not fit neatly into human timelines. Processes here unfold over geological scales. Sediment accumulates slowly, interrupted by sudden violent events. Chemical reactions proceed at rates that would feel static to surface observers. Biological growth is measured differently. Patience is not a virtue here. It is a requirement. For scientists accustomed to experiments that run for hours or days, this demands a shift in perspective. Understanding Challenger Deep often means accepting that answers may take decades to assemble, built from fragments of data collected under difficult conditions. Each mission contributes a small piece, rarely a complete picture. there is also the unsettling realization that Challenger Deep is not unique. It is simply the deepest known point. Other trenches exist. Other Hadal environments operate under similar pressures. If this one feels extraordinary, it is partly because it has been named, measured, and singled out. But it represents a class of environments that collectively make up a significant portion of Earth's surface. That realization reframes the planet itself. Earth becomes less a solid sphere with oceans on top and more a layered system where the majority of habitable space lies in conditions humans cannot endure. The surface becomes the exception rather than the rule. This inversion is difficult to sit with. It challenges the quiet assumption that our experience of Earth is representative of Earth as a whole. Challenger Deep exposes that assumption as convenience rather than truth. And yet, despite all of this, scientists continue to return to this place. Not because it feels familiar, but because it doesn't. Because it highlights the limits of current understanding. Because it forces questions that cannot be asked anywhere else. Because it demonstrates that Earth still holds environments that do not yield easily to explanation. The deepest place on Earth refuses to feel ordinary because it is not merely a location. It is a boundary. A boundary between what we can observe directly and what we must infer. Between environments shaped by sunlight and those shaped by pressure alone. Between the surface world we inhabit and the vast, largely unseen systems beneath it. As we move forward, the focus will narrow from the idea of depth itself to the specific geography that created this place, from abstraction to location, from scale to structure. Because understanding why Challenger Deep unsettles scientists requires knowing not just how deep it is, but where it sits, how it formed, and why this particular point on the planet became something so extreme. And that story begins not at the bottom, but along the edges of moving continents, where Earth quietly pulls itself apart and pushes itself together, one slow, relentless motion at a time. Finding Challenger. Deep on a map feels almost disappointing at first. After everything said about its depth and severity, after all the warnings about pressure and darkness, its location appears as a small, quiet marking in the Western Pacific Ocean. No dramatic symbol, no visual cue suggesting that this point represents the most extreme vertical distance on Earth. Just coordinates, a label, and a trench line curving gently across blue space. This contrast between significance and presentation is part of what makes Challenger Deep so unsettling. The map treats it as ordinary, reality does not. Challenger Deep lies within the southern end of the Mariana Trench, a massive geological feature stretching over 2,500 kilometres along the boundary where the Pacific Plate slides beneath the smaller Mariana Plate. This boundary is not a crack or a gap in the way people often imagine tectonic movement. It is a slow, grinding overlap, where one slab of Earth's crust is forced downward into the mantle. Over millions of years, this motion has carved a trench deeper than any other on the planet. On a global map, the Mariana Trench sits uncomfortably close to the edge. It appears far from continents, far from major shipping routes, far from population centres. This geographic isolation contributes to the sense that Challenger Deep exists beyond the usual frame of reference. It is not adjacent to familiar landmasses. It does not benefit from the contextual clues that help people orient themselves. It exists in a part of the ocean that feels peripheral, even though it plays a central role in Earth's geological machinery. Early maps of the Pacific Ocean did not show the trench at all. For centuries, cartographers filled that part of the world with blank space or decorative flourishes. The ocean was treated as a surface to be crossed, not a volume to be understood. Depth was irrelevant to navigation, as long as ships did not strike the bottom. The idea that the ocean floor could contain structures rivaling or exceeding the scale of mountains did not factor into early geographic thinking. The first hints of something unusual came with the advent of deep sea sounding in the late 19th and early 20th centuries. Using weighted lines lowered from ships, scientists began measuring ocean depth systematically. These measurements were slow, imprecise, and limited by technology, but they revealed something unexpected. In certain regions of the Pacific, the seafloor dropped far deeper than anticipated. Lines descended longer than anyone expected. Waits took unusually long to reach bottom. The numbers did not align with existing models of the ocean floor. Even then, Challenger Deep itself was not immediately identified. The trench was mapped gradually, point by point, with each sounding offering a fragment of the larger structure. It was not until sonar technology became more advanced that scientists could begin to visualize the trench as a continuous feature, rather than a series of isolated depth readings. Echo sounding allowed ships to send sound pulses downward and measure the time it took for echoes to return. This transformed depth measurement from guesswork into mapping. The name Challenger Deep comes from HMS Challenger, a British research vessel that conducted one of the first global oceanographic expeditions in the 1870s. Although the ship did not directly identify the deepest point with precision, its mission marked the beginning of systematic deep-sea exploration. Later measurements refined the data, and the deepest section of the trench was eventually named in recognition of that early effort. Despite this progress, the exact location of the deepest point has shifted slightly over time. Different surveys using different instruments and methodologies have produced slightly different results. Challenger Deep is not a single, perfectly defined spot. It is a region with several depressions clustered closely together. Determining which of these is truly the deepest depends on resolution, calibration, and interpretation. This uncertainty adds another layer of discomfort. Humans prefer definitive answers: a highest peak, a longest river, a deepest point. Challenger Deep resists that simplicity. It occupies a small area where differences of a few meters matter, but those differences are difficult to measure reliably under such extreme conditions. Even today, depth estimates vary slightly between missions. The location of Challenger Deep at the edge of tectonic plates also means it is subject to ongoing change. The seafloor here is not static. Subduction continues, sediment shifts, earthquakes reshape the trench walls. Over geological time, the deepest point may migrate. What is deepest today may not remain so indefinitely. This undermines the idea of permanence that maps often imply. Maps themselves contribute to the sense of distance. Most world maps are centered on land masses where people live. Oceans become background. They are colored uniformly, with depth indicated only by subtle shading, if at all. The Mariana Trench often appears as a thin line, easy to overlook. Challenger Deep becomes a label that requires intentional searching. It does not announce itself. This cartographic marginalization mirrors how humans relate to the ocean more broadly. We interact with its surface. We depend on it for climate regulation, food, and transport. But its interior remains conceptually distant. Challenger Deep exists at the far end of that conceptual distance. It is not just out of sight, it is out of mind. Finding it on a map requires effort. One must zoom in, switch layers, consult specialized bathymetric charts. Only then does the trench reveal its contours, its steep walls, its elongated shape. These maps, unlike standard atlases, are dense with information. They show gradients, slopes, and depth lines packed tightly together. In these representations, Challenger Deep begins to look less like a point and more like a wound. Bathymetric maps reveal that the trench walls are not smooth. They are jagged, fractured, and uneven. Slopes descend sharply, sometimes at angles steeper than mountain faces on land. In places, the seafloor drops thousands of meters over relatively short horizontal distances. This topography creates challenges not just for mapping, but for navigation during descents. Submersibles must contend with unpredictable terrain and limited visibility. The edge of the map feeling is reinforced by logistical realities. Reaching Challenger Deep requires long voyages across open ocean. Research vessels must travel days from the nearest ports. Supplies must be planned carefully. Weather windows must be respected. Once on site, operations depend on calm seas and precise coordination. There is little room for improvisation. If something goes wrong, assistance is far away. This remoteness affects how often the site is studied. Many oceanographic missions focus on more accessible regions, continental shelves, mid-ocean ridges, coastal zones. Challenger Deep demands disproportionate resources for limited data return. Funding agencies weigh cost against benefit. Time at sea is expensive. Equipment losses are common. As a result, missions to the deepest point are rare. The edge of the map's status also influences public perception. Space exploration captures imagination because it is framed as outward expansion. The deep ocean lacks that narrative momentum. It is inward, downward, hidden. Challenger Deep does not fit neatly into stories of progress. It does not promise easy rewards. It does not offer spectacle. It offers difficulty. For scientists, this difficulty is part of the appeal and part of the frustration. Locating Challenger Deep precisely, returning to it consistently, and comparing data across missions is challenging. Instruments must be calibrated carefully. Reference points are scarce. GPS does not work underwater. Positioning relies on acoustic systems that introduce their own uncertainties. Even defining the boundaries of Challenger Deep is not straightforward. The trench extends long distances, but the deepest region occupies a relatively small area. Pinpointing it requires integrating sonar data, pressure readings, and submersible observations. Each method has limitations. Sonar resolution decreases with depth. Pressure sensors drift. Visual confirmation is limited by lighting and sediment disturbance. This creates a situation where the deepest place on Earth is known, yet not known in the way other extreme points are known. There is no summit marker, no plaque, no stable reference. The bottom is soft sediment in places, compacted by pressure but still mobile. Submersibles leave impressions that may not last. The feeling of standing at the edge of the world is metaphorical, but it has practical implications. Challenger Deep represents a boundary of human capability. It is as far down as we can reasonably go with current technology. Beyond it lies no deeper point on Earth, but the conditions themselves already push materials and systems to their limits. Maps usually give the impression of mastery. They suggest that once something is labelled, it is understood. Challenger Deep undermines that assumption. It has a name and coordinates, yet it remains resistant to full comprehension. Its location is fixed only in a general sense. Its environment is dynamic. Its accessibility is limited. Its risks are persistent. Finding Challenger Deep on a map is easy. Understanding what that location represents is not. The edge of the map quality is also psychological. Humans tend to associate edges with endings. Beyond the edge lies uncertainty. Challenger Deep sits at the edge of our spatial understanding of Earth. It marks the limit of depth, the point where downward exploration cannot go further. That gives it a symbolic weight that exceeds its physical footprint. For scientists, working at this edge means accepting incomplete information. It means designing experiments that may fail. It means interpreting data that arrives fragmented and delayed. It means acknowledging that some processes may remain unobservable for the foreseeable future. This acceptance runs counter to the usual goals of science, which prioritize clarity, repeatability, and control. Challenger Deep offers none of these easily. It demands patience and humility. It forces researchers to confront the reality that Earth still contains environments that cannot be tamed by technology alone. As exploration continues, maps will become more detailed, resolution will improve, models will refine, but the fundamental challenge remains. Challenger Deep is not just hard to reach, it is hard to situate within human frameworks of understanding. Its location at the edge of the world map is not a cartographic accident. It reflects a deeper truth about how far removed this place is from everyday experience. From here, attention shifts from where Challenger Deep is to how depth itself behaves. Numbers begin to matter. Scale becomes oppressive. The concept of distance changes when vertical descent replaces horizontal travel. Understanding why scientists remain uneasy requires stepping beyond maps and into the physical reality of depth itself, where intuition begins to fail and pressure takes over as the defining force. Depth is a word that feels straightforward until it stops being one. At first, it behaves politely. A swimming pool has depth. A lake has depth. Even the open ocean, seen from the surface, feels deep in a way that is easy to imagine. You know water goes down. You know there is more below than you can see. But your intuition remains intact because your body, your senses and your everyday experiences still provide reference points. You can picture a rope. You can picture a diver. You can picture pressure increasing in a vague linear way. That intuition does not survive for very long once you begin descending past the layers of the ocean that humans are familiar with. At shallow depths, depth feels like distance. 10 meters down is 10 meters away from the surface. 20 meters is twice that. The relationship between numbers and experience still holds. You can equalize pressure in your ears, light still reaches you, sound behaves in recognizable ways. If something goes wrong, returning upward feels possible. But depth in the ocean is not linear in its effects, even if the measurements are linear on paper. Each additional meter adds weight, not metaphorical weight, but literal force. Water is heavy, and it stacks relentlessly. By the time you reach 100 meters, pressure is already more than 10 times what it is at sea level. At that point, the human body begins to struggle. Breathing compressed air becomes dangerous. Nitrogen narcosis affects judgment. Decompression limits become strict. This is where recreational diving ends, not because the ocean ends, but because human physiology does. Beyond that point, intuition begins to loosen. At 1,000 meters, sunlight has vanished completely. The ocean becomes a volume of cold darkness where vision is useless without artificial light. Pressure reaches roughly 100 atmospheres. Steel hulls must be thick. Electronics must be sealed. Any structure that relies on air-filled space becomes vulnerable. Yet 1,000 meters is still only the beginning. It feels deep to us because it is far beyond what we can experience directly, but in the context of the ocean, it is still part of the upper layers. What breaks human intuition is not a single threshold. It is the accumulation of thresholds that come faster than the mind expects. At 3,000 meters, pressure exceeds 300 atmospheres. At this depth, materials that feel solid and permanent on land begin to behave differently. Plastics harden or crack. Rubber seals stiffen. Metals flex in ways that are difficult to predict. Glass becomes a liability. Even carefully engineered equipment exists under constant stress. Not episodic stress, but unbroken, unrelenting force applied evenly from all directions. Human intuition evolved for environments where pressure differences are small and gradual. Even climbing a high mountain changes atmospheric pressure by only a fraction of what a few hundred meters of water does. There is no evolutionary framework for understanding what it means to exist under thousands of meters of ocean. The brain has no built-in reference for that kind of force. At 5,000 meters, the pressure is around 500 times atmospheric pressure. This is the depth where many submersibles reach their design limits. Beyond this, every additional meter compounds risk. There is no margin for error, no gradual failure. Structures either hold or they do not. What makes this especially difficult to grasp is that nothing looks dramatic from the outside. Pressure does not roar or flash. It does not announce itself. It simply exists, invisibly, doing work on every surface. A hull does not appear to be crushed. It is simply prevented from expanding outward. Inside, the environment may feel calm. Instruments may function normally. But the entire structure is one microscopic flaw away from catastrophic collapse. This disconnect between appearance and reality is where intuition fails most completely. Humans expect danger to look dangerous. We expect warning signs. In deep ocean environments, danger is silent and omnipresent. It does not escalate gradually. It waits. As depth increases further, numbers begin to lose meaning. Saying 6,000 meters does not feel significantly different from 7,000 meters in the mind, even though the difference in pressure is enormous. This flattening of perception is a cognitive limitation. Our brains are good at handling scales we encounter regularly. They are poor at handling extremes. At 10,000 meters, pressure exceeds 1,000 atmospheres. This is not an environment, it is a condition. Everything that enters it must be designed around pressure as the primary fact of existence. Shape matters more than material. Spheres are favoured because they distribute force evenly. Corners become points of failure. Seams become threats. Even then, no design is perfect. Submersibles intended for these depths are built with extraordinary care, but they remain temporary visitors. They are tolerated by the environment, not accommodated by it. Another aspect that breaks intuition is time. Descent to extreme depth takes hours. There is no sudden drop. There is no dramatic moment when everything changes. The transition is slow and continuous. Pressure increases steadily. Light fades gradually. Temperature drops. By the time a submersible reaches the deepest regions, it has passed through layers that each feel survivable on their own, even though the combined effect is lethal to unprotected life. This gradual transition masks the severity of the environment. If humans experienced depth the way they experience altitude, there would be clear milestones. But underwater, the absence of sensory cues creates a false sense of continuity. The mind does not register danger because nothing feels different in a visceral way. Sound contributes to this illusion. In water, sound travels faster and farther than in air. The ocean is not silent, even at great depth. There are low-frequency noises from distant earthquakes, ice cracking, and shifting sediments. These sounds create a sense of presence, even though nothing is visible. The environment feels active, not hostile. This activity can mislead intuition into perceiving familiarity where none exists. Temperature adds another layer. Deep ocean temperatures hover near freezing, but they are remarkably stable. There are no seasons, no daily cycles, no weather. The consistency can feel comforting, even though it is part of what makes the environment so alien. Stability at extreme conditions does not imply safety. It implies permanence. Another intuition failure comes from scale. On land, large distances are visible. Mountains dominate horizons, valleys stretch out. In the deep ocean, scale collapses visually. Visibility is limited to what artificial light reveals, often only a few meters. A steep trench wall might drop thousands of meters, but it appears as a dark slope fading into nothing. The mind cannot perceive its true size. This compression of visual information makes depth harder to internalize. Without a horizon or reference point, distance becomes abstract. A submersible might be hovering meters above the seafloor, or hundreds of meters above it, and the difference is not immediately apparent. Navigation relies entirely on instruments. Instruments, however, speak a language that does not always align with human intuition. Pressure gauges display numbers. Depth meters tick downward. These are symbolic representations. They require interpretation. They do not trigger instinctive responses. A reading of 10,900 meters does not activate the same caution mechanisms as standing near a cliff edge does. This mismatch between data and instincts is dangerous. It demands discipline and trust in systems rather than gut feeling. Scientists and pilots must learn to override intuition and rely on procedure. In extreme depth, intuition is not just unreliable, it is actively misleading. There is also the matter of reversibility. On land, most movements are reversible. You can walk back, you can retreat. In deep ocean descent, reversibility exists only as long as systems function. As depth increases, the energy required to ascend increases. Buoyancy systems must work perfectly. If ascent mechanisms fail, gravity and pressure offer no mercy. This creates a psychological asymmetry. Going down feels easier than coming back up. The descent is assisted by gravity. The ascent requires effort and functioning systems. This imbalance is subtle but important. It adds weight to every decision to descend further. Human intuition is also shaped by survival stories. We hear about climbers rescued from mountains. We hear about ships damaged but returning to port. Stories of failure at extreme depth are rarer because failure often leaves no survivors and little evidence. Equipment implosions are instantaneous. There is no drama, no struggle, just sudden absence. This absence feeds uncertainty. It is difficult to calibrate risk when consequences are absolute and poorly observed. Scientists must infer danger from physics rather than experience. They must imagine outcomes they have never witnessed. Depth also breaks intuition by challenging the idea of emptiness. The deep ocean is not empty. It is filled with water, pressure, organisms, chemicals, and movement. But it feels empty because it lacks the signals humans associate with life. No plants, no visible animals most of the time, no variation in light. This sensory deprivation alters perception. In such conditions, even experienced researchers report a sense of dislocation. Time feels stretched, attention narrows. The environment feels vast and confined at the same time. These psychological effects are not weaknesses. They are natural responses to environments the human brain was never meant to navigate. Another intuitive failure lies in comparisons. People often try to relate ocean depth to space. Both are hostile. Both require life support. Both are largely unexplored. But the analogy only goes so far. In space, pressure is absent. In the deep ocean, pressure is everything. In space, structures must withstand expansion. In the deep ocean, they must withstand collapse. This inversion matters. Materials behave differently. Failure modes differ. Human imagination, trained by science fiction and space exploration narratives, often underestimates how fundamentally different these environments are. Depth is not emptiness. It is compression. The breaking point for intuition often arrives not as fear but as confusion. Researchers accustomed to clear cause and effect relationships encounter data that behaves unexpectedly. Instruments drift, readings fluctuate, chemical processes occur that seem out of place, biology adapts in ways that contradict surface logic. At extreme depth, even water itself behaves differently. Its compressibility, usually negligible in everyday contexts, becomes significant. Density changes affect circulation. Chemical solubility shifts. These are subtle effects, but they accumulate. Models that work at shallower depths must be adjusted. Assumptions must be questioned. What finally shatters intuition is the realization that there is no natural limit visible from within the system. As depth increases, there is no signal that says, "This is too deep." There is no warning threshold built into the environment. The only limit is imposed by human design and tolerance. That makes the deepest places on Earth psychologically unsettling. They do not push back in recognizable ways. They do not threaten with noise or movement. They simply exist beyond the range where human instincts are useful. For scientists, this means learning to operate without intuition as a guide. Decisions must be based on calculations, margins, and redundancy. Emotional responses must be acknowledged but not trusted. Comfort becomes a liability. Familiarity becomes dangerous. Depth becomes not just a measurement, but a condition that reshapes how thinking itself must operate. As understanding of depth improves, numbers become more precise, models more accurate, and technology more capable. But the intuitive gap remains. No amount of data can make 10,000 meters feel real in the body. No visualization can fully convey what it means to exist under that much water. And this is where the discomfort deepens, because if intuition fails here, then understanding must proceed without it. That leaves scientists relying on abstraction, simulation, and indirect observation to explore a place that does not forgive misinterpretation. From this point, the discussion shifts naturally toward what depth actually does to the physical world, not to perception, but to matter itself. Because once intuition is stripped away, what remains is physics, uncompromising and exact, shaping everything that enters the deepest parts of the ocean, whether we understand it fully or not. Pressure is one of those concepts that feels manageable until it becomes absolute. At the surface, pressure is background noise. The weight of the atmosphere presses down constantly, but our bodies are adapted to it so completely that we don't feel it. We only notice pressure when it changes suddenly, during a flight, a dive, or a fast-moving storm. Even then, the sensation is mild, temporary, and easily relieved. This everyday familiarity gives us the false impression that pressure is a flexible condition, something that can be tolerated, adjusted to, or escaped. That impression does not survive contact with the deepest parts of the ocean. At extreme depth, pressure is not an environmental feature. It is the defining force. Everything that exists there exists under pressure first and foremost. Shape, structure, chemistry, and behaviour are all subordinate to it. In places like Challenger Deep, pressure is not something acting on objects. It is something objects must be built around entirely. To understand what that means, it helps to abandon familiar comparisons early. Saying that pressure at the bottom of the trench is over 1,000 atmospheres is technically accurate, but it does very little to communicate reality. Numbers like that exist outside lived experience. A more useful approach is to think in terms of force, applied relentlessly and uniformly from every direction without pause. At sea level, air molecules push against your body lightly. At depth, water molecules do the same thing, but water is far denser than air. Each additional meter adds another layer of weight. By the time you reach 10,000 meters, that weight has accumulated into a force capable of collapsing steel, crushing ceramics, and deforming materials that feel rigid and immovable on land. One of the most counterintuitive aspects of pressure at this scale is that it does not attack in obvious ways. There is no bending, no creaking, no gradual warning signs. Materials under extreme pressure often fail suddenly. A structure can appear perfectly stable until the instant it is not. Failure is catastrophic, not incremental. This is why deep-sea engineers are so cautious about materials that behave well under tension but poorly under compression. On land, we design bridges and buildings to resist forces pulling outward or downward. In the deep ocean, everything is pushed inward. Air-filled spaces are liabilities. Even tiny voids can become points of collapse. Glass is a good example. At the surface, glass feels strong. It resists scratching. It holds shape. Under extreme pressure, it becomes brittle and unpredictable. A window that would easily withstand storms at sea level can implode instantly at depth. This is why deep-sea submersibles use thick acrylic spheres instead of traditional glass. Acrylic deforms slightly under pressure rather than shattering, distributing force instead of concentrating it. Even metals behave differently. Steel alloys chosen for deep-sea use are selected not just for strength, but for how they respond to long-term compression. Some metals fatigue faster under constant pressure. Others experience microscopic changes in crystal structure that weaken them over time. These changes are invisible to the naked eye, but significant enough to compromise safety. Pressure also alters the behavior of fluids. Water itself becomes slightly compressible at extreme depth, a property that is negligible at the surface. This compressibility affects circulation patterns, density gradients, and chemical solubility. Gases dissolve differently. Chemical reactions proceed at altered rates. Assumptions made at shallower depths stop being reliable. For scientists, this means that pressure is not just a hazard to survive. It is a variable that must be understood as an active participant in every process observed. Electronics, for example, are not immune. Circuit boards must be sealed inside pressure-resistant housings. Even then, pressure can affect insulation materials, solder joints, and connectors. Tiny imperfections that would never matter on land become critical failure points. Water intrusion is not gradual. At extreme pressure, it is explosive. A seal that fails does not leak. It gives way completely. Pressure also complicates temperature management. At depth, water temperature is cold but stable. Heat generated by electronics has nowhere to go easily. Thermal gradients behave differently under pressure. Cooling systems must be designed carefully to avoid overheating in an environment that feels, paradoxically, cold. Another effect of pressure that resists intuition is its interaction with time. Materials under constant high pressure experience creep, a slow, permanent deformation that occurs even when stress levels remain below the material's nominal strength. Over long periods, shapes change subtly, seals loosen, fits degrade. This means that equipment rated for a certain depth may not remain safe indefinitely, even if it never exceeds that depth. This is one reason why repeat descents are treated cautiously. A submersible that survives one trip to the bottom of the trench is not automatically cleared for another. Each exposure accumulates damage at scales too small to detect easily. Engineers must assume that the ocean remembers. Pressure also affects sound. In the deep ocean, sound travels faster and farther, but its behaviour changes with depth and density. Low-frequency sounds propagate efficiently, while higher frequencies are absorbed. This creates an acoustic environment that feels distant and distorted. Instruments designed to communicate or navigate using sound must account for these changes. A signal that works perfectly at one depth may behave unpredictably at another. This matters because sound is the primary means of sensing and communication in the deep ocean. Light is ineffective. Radio waves do not travel well through water. Pressure, therefore, indirectly shapes how scientists observe the environment. It influences what can be detected, how quickly information travels, and how accurately positions can be determined. Biology, too, is reshaped by pressure in ways that challenge assumptions. Proteins, for example, are sensitive to pressure. Their three-dimensional shapes determine their function, and extreme pressure can cause those shapes to collapse or misfold. Life at great depth has evolved proteins that remain stable under conditions that would destroy surface organisms. Cell membranes are composed differently. Enzymes operate at altered rates. This adaptation does not imply comfort. It implies survival under constraint. Deep-sea organisms are not thriving in a gentle environment. They are enduring conditions that push chemistry to its limits. Even bones and shells are affected. Calcium-based structures behave differently under pressure and low temperature. Some organisms abandon rigid skeletons altogether in favour of softer, more flexible forms that distribute stress evenly. This is why many deep-sea creatures appear gelatinous or fragile when brought to the surface, even though they are perfectly adapted to their native environment. When pressure is removed suddenly, as happens when organisms are brought up too quickly, tissues rupture, gases expand violently, structures collapse. This makes direct study difficult. Many deep-sea species cannot survive decompression, leaving scientists to rely on remote observation and indirect analysis. Pressure also interacts with geology in unsettling ways. At the bottom of trenches, immense pressure affects how rocks fracture and flow. Combined with tectonic stress, it influences earthquake behaviour. Faults behave differently at depth than they do near the surface. Energy is stored and released in patterns that are still not fully understood. Sediments at the bottom of Challenger Deep are compacted into dense layers. Pore spaces shrink. Fluids trapped within sediments are pressurized. When disturbed, these sediments can behave unpredictably, flowing like liquids or collapsing suddenly. Submersibles must be careful not to stir the seafloor excessively, as even small disturbances can obscure visibility or damage instruments. The cumulative effect of pressure on matter, creates an environment where nothing can be taken at face value. Materials that are safe elsewhere are dangerous here. Processes that are slow elsewhere accelerate or destabilize. Assumptions that hold at moderate depths break down completely. This is why scientists speak about pressure in the deep ocean with a tone that borders on respect. It is not fear in the dramatic sense, it is recognition. Pressure does not negotiate. It does not fluctuate with weather. It does not provide grace periods. It is constant, impartial, and exact. In practical terms, this means that exploration of extreme depth is constrained by engineering limits rather than scientific curiosity. There are questions researchers would like to answer that remain out of reach, simply because instruments cannot survive long enough or function reliably under such conditions. Data gaps are not always due to lack of effort. They are due to the environment enforcing boundaries. Even human presence, when it occurs, is fleeting. Crewed submersibles descend, observe briefly, and ascend. There is no lingering, no extended habitation. Pressure makes the idea of a deep-sea base at such depths effectively impossible with current technology. Life support systems would need to withstand not only pressure, but the consequences of any failure under that pressure. This impermanence shapes how science is done. Experiments must be short. Observations must be efficient. There is little room for adjustment once a descent begins. Decisions made at the surface carry consequences hours later, when reversal is no longer simple. Pressure also changes how scientists think about safety. On land, safety often involves redundancy and gradual failure modes. In the deep ocean, redundancy helps, but failure modes remain abrupt. There is no controlled collapse. Implosion happens at the speed of sound. Survival is not a question of endurance, but of prevention. This knowledge sits quietly behind every design choice. It informs the thickness of hulls, the shape of vessels, the placement of sensors. It dictates conservatism. Over-engineering is not wasteful here, it is necessary. What makes pressure beyond imagination truly unsettling is not just its magnitude, but its consistency. It never turns off, it never relaxes, it is always present, always working. Any moment of inattention, any overlooked detail, is eventually corrected by force. For scientists, this creates a relationship with the environment that is fundamentally asymmetrical. The ocean does not adapt to us. We adapt to it temporarily, cautiously, and incompletely. As exploration continues, materials improve, modelling becomes more accurate, but pressure remains the ultimate gatekeeper. It defines what can be done, how often it can be done, and at what cost. Understanding pressure at these depths is not just an academic exercise. It is essential for interpreting every observation made there. Without accounting for pressure, data is meaningless. Life, chemistry, and geology all look different when viewed through the lens of force applied relentlessly over kilometers of water. And once pressure is understood not as a number but as an omnipresent condition, the next question becomes unavoidable. If matter itself is reshaped by depth, then what happens to light, energy, and visibility in a place where pressure and darkness combine to erase the most basic cues humans rely on to understand their surroundings? Sunlight feels so constant at the surface that it's easy to forget how fragile its reach really is. We treat daylight as a given, something that simply exists wherever we go, filtered perhaps by clouds or time of day, but always present in some form. Even underwater near the surface, sunlight still seems dependable. It bends, scatters, shimmers. It turns the ocean blue and green and gives life its familiar visual cues. This creates the illusion that light is a persistent companion, capable of following us almost anywhere. That illusion fails completely long before the deepest parts of the ocean begin. By the time you reach the region above Challenger Deep, sunlight is no longer fading. It is already gone. Not dimmed, not weakened, not hidden behind distance, but fully extinguished. No ray of sunlight has ever reached the bottom of this place. Not once, not indirectly, not during any seasonal shift or climatic anomaly. The geometry of the Earth, the physics of light, and the structure of water make that impossible. Understanding why requires stripping sunlight of its familiarity and looking at it as a physical phenomenon rather than a comforting presence. Sunlight is electromagnetic radiation. It travels in straight lines unless something interferes with it. In the vacuum of space, it can cross enormous distances with little loss. But water is not a vacuum. It is dense, structured, and filled with particles that interact with light in complex ways. When sunlight enters the ocean, it immediately begins losing energy. Some wavelengths are absorbed almost instantly. Others scatter in multiple directions, bouncing between molecules until they dissipate. Red light is the first to disappear. Within the first few meters, reds are gone, which is why underwater photographs quickly lose warm tones. Orange and yellow follow. Green persists a little longer. Blue travels the farthest, not because it is stronger, but because water absorbs it less efficiently. This is why the open ocean appears blue from above. It is not reflecting the sky so much as selectively preserving the wavelengths that survive longest. But even blue light has limits. By around 200 meters, the ocean enters what scientists call the twilight zone. Here, light is weak, scattered, and directionless. Shapes blur. Contrast disappears. Photosynthesis becomes nearly impossible. Life adapts by becoming efficient, sensitive, or reflective. But even this dim environment is temporary. Below roughly 1,000 meters, sunlight is entirely absent. This is the aphotic zone. The word does not mean dark in a poetic sense. It means without light. There is no dawn here, no dusk, no shadow, no variation. The absence is absolute and permanent. Challenger. Deep lies far below this boundary, thousands of meters beneath a zone that is already completely dark. Even if sunlight could somehow bend around the curvature of the Earth or pass through kilometers of water without being absorbed, the geometry alone would prevent it from reaching such depth. The ocean simply blocks it. This absence of sunlight does more than remove visibility. It removes an entire framework of interaction. On the surface, sunlight drives climate, weather, and ecosystems. It powers photosynthesis, which forms the base of most food webs. It establishes daily rhythms. It provides warmth. It defines direction. At the bottom of the trench, none of that applies. There is no photosynthesis, no plants, no algae, no phytoplankton drifting down light-filled currents. Any life that exists there must rely on energy sources that do not originate from sunlight directly. This fundamentally alters how ecosystems function. Instead of being driven by production at the surface, deep environments depend on what falls from above or what emerges from below. Organic material sinks slowly from surface waters, drifting downward like snow. By the time it reaches extreme depths, it is sparse, degraded, and unpredictable. This marine snow provides only intermittent nourishment. Life that depends on it must be patient, efficient, and capable of surviving long periods with very little input. In some areas, chemical energy replaces solar energy. Hydrothermal vents release minerals and heat from beneath the Earth's crust. Chemosynthetic organisms use these chemicals to fuel metabolic processes, but even these systems are rare and localized. Challenger Deep itself is not known for abundant vent activity. Life there exists in a state closer to endurance than abundance. The absence of sunlight also removes one of humanity's primary investigative tools. Vision is our dominant sense. We interpret the world through light, colour, and shape. In Challenger Deep, vision is useless without artificial illumination. Every image ever captured there has been created by human-made light sources, carried down temporarily and powered by finite energy. This has consequences. Artificial light does not behave like sunlight. It is directional, limited in range, and prone to reflection. Sediment stirred up by movement quickly clouds visibility. fine particles suspended in water scatter light back toward the source, creating a kind of visual fog. The brighter the light, the worse the scattering becomes. As a result, images from the deepest parts of the ocean often feel incomplete or distorted. Objects emerge suddenly from darkness, then vanish just as quickly. Scale is hard to judge. Distance collapses. What appears close may be meters away. What appears large may be small and nearby. This visual uncertainty feeds scientific caution. Observations must be interpreted carefully. Context is limited. The absence of ambient light removes background information that would otherwise help situate what is being seen. Sunlight also provides timekeeping cues. On the surface, organisms track day and night cycles. Even deep-sea creatures living hundreds of meters down may respond indirectly to surface rhythms through changes in temperature or food availability. At the bottom of Challenger Deep, such cues are absent. Time, biologically speaking, becomes unanchored. Organisms here do not experience days. They do not experience seasons. Their internal rhythms, if they exist, are decoupled from the sun entirely. This raises questions scientists are still exploring. How do biological clocks function without light? What replaces the role of day-night cycles in regulating behaviour, reproduction, and metabolism? The answers are not straightforward. Some organisms appear to operate on chemical cues. Others respond to pressure changes caused by distant tides or seismic activity. Some may simply exist in a state of metabolic minimalism, reacting only when conditions change enough to matter. From a geological perspective, the absence of sunlight also means the seafloor remains cold and thermally stable. Without solar heating, temperature gradients are shallow. Heat comes primarily from Earth's interior or from slow mixing with overlying waters. This stability influences chemical reactions, mineral formation, and sediment behaviour. Sunlight, when present, can drive photochemical reactions. It can break molecules apart or trigger new bonds. In Challenger Deep, such reactions do not occur. Chemistry follows different pathways. Processes are slower. Energy barriers are crossed differently. This alters how elements cycle through the environment. For scientists studying these processes, the lack of sunlight simplifies some variables while complicating others. There is no need to account for diurnal heating or photodegradation, but there is also no easy energy source to explain observed activity. Life and chemistry must be traced back to non-solar origins. The psychological effect of permanent darkness should not be underestimated either. Even though submersibles bring their own light, the awareness that nothing exists beyond that narrow cone of illumination affects perception. The environment feels bounded and unbounded at the same time, bounded by what can be seen, unbounded by what lies beyond the light's reach. Pilots and researchers often describe a heightened sense of focus in such conditions. Distractions fall away, attention narrows. This can be useful, but it can also be disorienting. Without visual landmarks, orientation relies entirely on instruments. Direction becomes conceptual rather than intuitive. The darkness also hides motion. Currents exist at depth, but they are slow and subtle. Without light to reveal drifting particles, movement can be imperceptible. The environment may appear static even when it is not. This can lead to misinterpretation. A stationary object may be moving relative to the seafloor. A submersible may be drifting without realizing it. Sunlight also shapes human culture in ways that are easy to overlook. Our language, metaphors, and assumptions are light-based. We speak of illumination, clarity, and insight. Darkness is associated with uncertainty. These associations persist even in scientific contexts. Working in an environment where darkness is absolute challenges these ingrained patterns. In Challenger Deep, uncertainty is not something to be eliminated through observation alone. It is an inherent condition. Light cannot fully penetrate it. Knowledge arrives in fragments, illuminated briefly, and then surrounded again by unknowns. This is part of why the place continues to unsettle scientists. It is not just physically inaccessible, It is epistemologically resistant. The absence of sunlight removes one of our most powerful tools for understanding and replaces it with dependence on instruments that must survive pressure, darkness, and distance. Even when data is collected successfully, interpreting it requires caution. Without the broader context provided by light, spatial relationships are harder to establish. Biological interactions are harder to observe directly. Geological features must be inferred from partial scans and limited imagery. The permanence of darkness also means that nothing at the bottom has ever been visually influenced by the sun. There are no faded colours, no sun-bleached surfaces, no shadows cast by passing clouds. The environment exists in a state that has never known illumination. This is not a temporary condition. It is the baseline. That realization has implications beyond Earth. Scientists studying extreme deep-sea environments often draw cautious parallels to conditions on other worlds. Moons like Europa or Enceladus, with subsurface oceans hidden beneath ice, may share some characteristics with Earth's deepest trenches. Understanding how life and chemistry function without sunlight here informs hypotheses about life elsewhere. But even without looking outward, Challenger Deep forces a re-evaluation of Earth itself. It reveals that vast portions of the planet operate independently of the sun's direct influence, that life, motion, and change persist without light challenges surface-centric views of habitability. For all of these reasons, the fact that sunlight has never reached this place is not just a curiosity. It is a defining feature. It shapes everything from biology to geology to human perception. It ensures that Challenger Deep remains fundamentally alien, even though it lies beneath familiar waters. And once light is removed from the equation, another question naturally follows. If vision is useless and sunlight irrelevant, how do humans even begin to explore such a place? And what happens when the first descent moves beyond darkness and into the silence where only machines can go? The first descent toward Challenger Deep did not begin with drama. There were no sudden drops, no cinematic rush into darkness, no instant transformation of the world outside. Instead, it began the way most deep-sea journeys begin, with patience, procedure, and a long checklist of things that had to go exactly right. On the surface, the ocean looked ordinary. Waves rose and fell, instruments were calibrated, voices moved calmly between technical terms and quiet confirmations. Nothing in that moment suggested that the journey ahead would mark a boundary humans had never crossed before. The descent itself unfolded slowly. A submersible does not plunge. It sinks deliberately, guided by ballast and controlled buoyancy. Gravity assists, but gravity is not trusted on its own. Every meter downward is monitored. Every system is checked again and again. At first, the water outside still carried traces of surface life. Light filtered down faintly. Particles drifted past viewports. The environment felt distant but not alien. As the vehicle moved deeper, those cues faded. Light weakened, then scattered, then disappeared entirely. The last hint of blue dissolved into black. Artificial lights became the only source of vision, cutting narrow cones through water that swallowed illumination almost immediately. Outside those cones, nothing existed in visual terms. Not emptiness, but unknowability. Pressure increased steadily, though nothing inside the submersible reflected that change. The interior remained stable, quiet, and controlled. Instruments reported rising numbers. Gauges ticked downward. The environment inside felt unchanged, and that contrast mattered. It created a sense of separation that was both reassuring and deceptive. Everything felt normal because the systems were working. The danger was not felt. It was calculated. Communication with the surface continued for a time, carried by acoustic signals that travelled slowly through the water. Messages were short, efficient and deliberate. There was no casual conversation. Words were chosen carefully, time stretched between transmissions. The deeper the descent went, the longer the delays became. Responses arrived seconds later, then minutes later. The connection grew thin. Eventually, even that connection weakened. Sound behaves differently at extreme depth. Pressure and temperature gradients bend acoustic paths. Signals refract, scatter, and attenuate. At some point, reliable communication becomes intermittent. The submersible is no longer in constant contact with the world above. It is still technically connected, but practically isolated. That is when the silence began to take over. This silence was not the absence of sound in a literal sense. The ocean is never truly silent. Low-frequency vibrations travel vast distances. The planet hums quietly with tectonic motion, distant seismic activity, and the slow shifting of water masses. These sounds exist, but they are not recognizable. They do not resemble surface noise. They feel more like pressure changes than sound waves. Inside the submersible, mechanical noises persisted. Fans circulated air, pumps adjusted systems, instruments clicked and whirred. These sounds became disproportionately important. They were familiar, they indicated function. They reassured the occupants that systems were alive and responsive. Outside, there was nothing to hear that could be easily interpreted. As the descent continued, the seafloor did not appear gradually. There was no horizon rising to meet the vehicle. Instead, darkness remained unbroken until the lights finally revealed texture where none had existed before. Sediment came into view as a pale, uneven surface reflecting artificial light weakly. Shadows appeared for the first time in hours. This moment marked a transition that was subtle but profound. The journey had reached the bottom of something, not metaphorically but physically. Below lay no further descent. Above lay kilometres of water. The silence at this point took on a different quality. Communication with the surface, already delayed, became minimal. Messages were brief, sometimes distorted. The submersible existed in a kind of temporal bubble, operating on its own internal schedule. Every action was deliberate, every movement was slow. The margin for error had narrowed to nearly nothing. What made this silence unsettling was not fear in the conventional sense. It was the realization that the environment did not acknowledge the presence of the submersible in any meaningful way. There was no reaction, no disturbance beyond the faint clouds of sediment stirred by thrusters. The seafloor did not resist. It did not respond. It simply existed. This indifference is difficult to articulate because it contradicts how humans usually experience exploration. On land, environments push back, weather changes, terrain challenges movement. In space, systems must constantly correct for velocity and orientation. In the deepest ocean, the environment does not interact in obvious ways. It overwhelms passively. Silence, in this context, was not calm. It was totality. It was the absence of reference. Without sound cues, without visual landmarks beyond the immediate area, orientation became purely instrumental. Direction was defined by numbers, not by sensation. Movement had to be inferred. The first descent also revealed something unexpected. The bottom of the trench was not smooth or uniform. It was irregular, shaped by landslides, sediment flows and tectonic stress. Fine particles covered the surface, compacted by pressure into a dense layer that behaved neither like loose sand nor solid rock. Touching it stirred clouds that lingered, slow to settle. This behaviour further complicated observation. Once disturbed, the environment obscured itself, visibility dropped, features vanished behind suspended sediment. The lights that revealed the seafloor also made it harder to see clearly. This created a paradox. To observe, light was required. To move, propulsion was required. Both of these actions degraded the very conditions needed for observation. The deeper the exploration went, the more delicate the balance became. Silence also extended to the absence of biological noise. Near the surface, life announces itself constantly. Fish move, creatures interact, Soundscapes are busy. At extreme depth, life exists, but it does not broadcast itself. Movements are slow, populations are sparse, interactions are rare. When organisms appeared in the lights, they did so briefly. A shape crossing the beam, a movement at the edge of vision, then nothing again. The silence swallowed them as quickly as it revealed them. For the people inside the submersible, this required a shift in attention. Waiting became part of observation. Long stretches passed where nothing changed visually. Instruments recorded data continuously, but sensory input remained minimal. This kind of environment tests concentration in a way that busy settings do not. The mind must remain alert without stimulation. Time perception altered subtly. Minutes felt longer. Tasks expanded to fill available attention. Without external cues, internal rhythms took over. This was not disorientation, but recalibration. The silence also highlighted the fragility of human presence. Inside the submersible, life depended entirely on systems functioning as designed. Oxygen supply, power, hull integrity. Any failure would unfold without warning and without external rescue. The silence outside was a reminder that nothing beyond the vessel could intervene. This awareness did not produce panic, it produced focus. Procedures mattered, checklists mattered, redundancies mattered. Every action was deliberate not because of fear, but because the environment demanded precision. The first descent also marked a psychological boundary. Reaching the deepest point on Earth did not feel like conquering something. There was no sense of arrival in the traditional sense. There was no summit moment. The bottom did not feel like a destination. It felt like a limit. This distinction matters. Humans often frame exploration as progress toward a goal. Challenger. Deep reframed it as contact with an extreme condition. The objective was not to stay, not to claim, not to alter, but to observe briefly and then leave. Silence reinforced that impermanence. Nothing invited lingering. There was no shelter, no place to anchor. The environment offered no affordances beyond what the submersible brought with it. Even recording data felt provisional. Sensors captured readings, cameras recorded images, samples were collected carefully. But all of it felt temporary. The environment would continue unchanged long after the submersible departed. The silence would remain. As ascent began, the silence did not immediately lift. Communication remained limited. Visual cues faded again as the seafloor dropped out of sight. Darkness reclaimed the space. Pressure decreased slowly, but the environment outside remained unchanged for a long time. Only after rising thousands of meters did light begin to return faintly. Only then did the ocean start to resemble something familiar again. Only then did sound begin to carry recognizable patterns. The memory of the silence, however, persisted. For scientists, that first descent did more than confirm measurements. It confirmed that some environments do not accommodate human presence in any meaningful way. They tolerate it briefly, without acknowledgement, and then resume their own rhythms. This realization shaped subsequent exploration. It influenced design choices, mission planning, and expectations. It reframed Challenger Deep not as a place to be mastered, but as a condition to be respected. Silence became a defining feature, not because it was absolute, but because it stripped away assumptions. It forced reliance on instruments. It demanded patience. It highlighted vulnerability. As exploration continued, machines would take on a larger role, entering places humans could not safely go, and staying longer than humans ever could. These machines would bring back data, images, and samples, but they would also return changed in subtle ways shaped by the environment they entered. That transition, from human descent to machine endurance, marked the next phase of exploration. It shifted the focus from momentary presence to sustained observation, and from human sensation to mechanical resilience. Machines are the only reason humans know as much as they do about Challenger Deep. Without them, the deepest parts of the ocean would remain almost entirely theoretical, defined by equations, indirect measurements, and cautious speculation. Machines are what allow observation to persist beyond the brief window of a human descent. They carry cameras, sensors, samplers, and recorders into places where people cannot stay, and they do so repeatedly, quietly, and without complaint. But the machines that go down into the deepest trench do not come back unchanged. This is not a metaphor. It is a practical, recurring reality of deep-sea exploration. Even when machines survive, even when they complete their missions and are recovered successfully, they often return altered in ways that are subtle, cumulative, and difficult to predict. The ocean does not simply test machines, it imprints on them. At first glance, a deep-sea vehicle looks similar to any other scientific instrument. It has housings, connectors, power systems, and control electronics. It is assembled in workshops under clean conditions. It is tested under simulated pressure. Engineers calculate tolerances. Safety margins are built in. Everything about the design suggests control. That sense of control diminishes rapidly once the vehicle leaves the surface. The descent subjects machines to an environment that cannot be replicated perfectly in laboratories. Pressure chambers can simulate force, but they cannot fully reproduce the combined effects of pressure, cold, chemical exposure, time, and motion. In the real ocean, these factors interact continuously. Materials respond not just to force, but to duration. Systems are stressed not just by magnitude, but by persistence. One of the first things engineers notice after recovery is deformation. Not dramatic bending or crushing, but small changes. Slight warping of panels, compression of seals, changes in the fit of components that were once precise. These alterations may not compromise function immediately, but they matter. They indicate that the machine has been pushed beyond the conditions it was designed to experience repeatedly. Pressure works at every interface. Any place where two materials meet becomes a potential failure point. O-rings flatten, adhesives creep. Fasteners experience micro-movements. Over time, these changes accumulate. A vehicle that survives one descent may be significantly weaker afterward, even if no damage is obvious. Electronics tell a similar story. Circuit boards exposed to extreme pressure are sealed inside protective housings, but pressure still finds indirect ways to exert influence. Insulation materials behave differently. Tiny air pockets compress. Solder joints experience stress. Electrical noise patterns shift. After recovery, engineers often find that systems still function, but not exactly as before. Sensors are particularly vulnerable. Instruments designed to measure pressure, temperature, chemistry, or biological signals rely on calibration. That calibration assumes stable relationships between components. Extreme pressure alters those relationships. A sensor may still produce data, but its accuracy may drift. Determining whether a change reflects the environment or the instrument becomes an ongoing challenge. Cameras face their own problems. Housings must withstand immense force while maintaining optical clarity. Acrylic viewports may deform slightly, altering focal properties. Tiny scratches become stress concentrators. Light housings suffer from sediment abrasion. After multiple dives, image quality often degrades in ways that are hard to correct. Even mechanical systems, which seem robust, are affected. Thrusters operating in dense, cold water under pressure experience altered fluid dynamics. Bearings behave differently. Lubricants thicken. Moving parts encounter resistance that does not exist at shallower depths. After recovery, engineers may find increased wear, reduced efficiency, or unexpected noise. One of the most challenging aspects of this transformation is that it is not uniform. Two identical machines sent on similar missions may return in noticeably different condition. Small variations in trajectory, depth profile, or time spent near the seafloor can produce disproportionate effects. The environment amplifies small differences. This unpredictability complicates planning. Engineers cannot rely solely on design specifications. They must incorporate experience, pattern recognition, and conservative assumptions. Vehicles are often overbuilt not because engineers are unsure of the physics, but because they know the physics will express itself in ways that models cannot fully anticipate. Uncrewed vehicles in particular face harsh trade-offs. To reach extreme depths, they must be compact and strong. Redundancy adds weight and complexity. Every additional system increases the chance of failure. Designers must choose between capability and survivability, often compromising both. When machines fail at depth, the failure is usually final. Implosion occurs in milliseconds. There is no distress signal, no partial recovery. The vehicle is reduced to fragments scattered across the seafloor. Data stored on board may be lost entirely. This makes each mission a calculated risk. Even when machines return intact, the data they carry reflects the environment's influence. Measurements may show anomalies that require careful interpretation. Is a chemical gradient real? Or did pressure alter the sensor? Is a biological observation representative? Or was the organism disturbed by the vehicle's presence? Is a geological feature stable? Or was it reshaped by the mission itself? These questions are not academic. They affect conclusions. They determine whether findings can be generalized or must be treated as isolated observations. There is also the issue of contamination. Machines carry traces of the surface world with them. Oils, metals, microbes. At extreme depth, where ecosystems are sparse and slow to recover, even small disturbances matter. Engineers take steps to minimize contamination, but it cannot be eliminated entirely. The act of observation changes the environment, if only briefly. This awareness adds another layer of responsibility. Machines are not neutral observers. They are intruders, tolerated temporarily. Their design must balance durability with restraint. One of the most striking examples of machines returning changed is the loss of acoustic performance. Hydrophones and sonar systems calibrated at the surface may behave differently after repeated exposure to pressure. Sensitivity shifts, background noise profiles change. Interpreting long-term acoustic data requires accounting for instrument drift, caused not by malfunction, but by environmental imprint. Over time, researchers have learned to expect this. Post-mission analysis includes not just data review, but forensic examination of the vehicle itself. Engineers look for patterns. Which components fail first? Which materials age poorly? Which designs tolerate repeated exposure? This iterative process drives innovation, but it is slow and expensive. Each improvement is hard-won. Each failure teaches a lesson at significant cost. The ocean, in this sense, becomes a collaborator in design. It forces adaptation. It rejects assumptions. It shapes technology through attrition rather than feedback. There is also a psychological dimension to relying on machines that may not come back the same. Researchers must trust instruments that they know are being altered by the very environment they are studying. This requires humility. Data is never taken at face value. Everything is contextualized. Long-term monitoring is especially difficult. Instruments deployed for months or years at great depth often show gradual degradation. Power systems weaken, sensors drift, communications falter. Recovering these instruments is itself a challenge, and sometimes impossible. Lost equipment becomes part of the seafloor, silent and inert. Despite this, machines remain indispensable. They extend observation beyond human limits. They allow repeated visits. They collect continuous data. Without them, Challenger Deep would remain largely unknown. But the cost of this knowledge is acceptance that machines are not immune. They are shaped by the environment as much as they shape our understanding of it. This reciprocal relationship changes how exploration is framed. Instead of conquering the deep, scientists learn to negotiate with it. Instead of imposing design, they respond to feedback delivered through wear, distortion, and failure. As technology improves, materials become stronger, electronics more resilient, and designs more refined. But the fundamental reality remains. The deepest ocean is not a place where machines operate unchanged. It is a place where machines are tested at the limits of matter itself, and this realization leads naturally to another unsettling question. If machines struggle to survive here, and if the environment reshapes even our most advanced tools, then what does that imply about the forms of life that exist there permanently, adapting not over missions or years, but over evolutionary time spans that make machine lifetimes seem insignificant? For a long time, the deepest parts of the ocean were assumed to be nearly lifeless, not because scientists lacked imagination, but because the conditions seemed fundamentally incompatible with biology, as it was understood. No sunlight, near-freezing temperatures, crushing pressure, scarce energy. These were not challenges to be adapted to, but barriers that appeared absolute. Life, according to surface-based logic, needed light, warmth, and relatively gentle physical conditions. Remove those, and complexity should collapse. And yet, at the bottom of Challenger Deep, life exists. This fact alone unsettled early oceanographers, and it continues to unsettle scientists today, not because life is present, but because of how it is present. The organisms found at extreme depth do not merely tolerate the environment. They are shaped by it in ways that undermine long-held assumptions about what life requires and how it functions. The first hints came not from direct observation, but from indirect evidence. Samples retrieved from deep trenches contained traces of biological material. Later, cameras captured fleeting images of movement at depths once thought sterile. Each discovery forced a reassessment, not just of deep-sea biology, but of the boundaries scientists had drawn around life itself. What makes this life particularly difficult to reconcile with intuition is that it exists without the foundational energy source that supports nearly all surface ecosystems. Sunlight does not reach these depths. Photosynthesis does not occur. There is no primary production in the traditional sense. Instead, life persists on energy that arrives indirectly, sporadically, or from chemical sources deep within the earth. Much of the biological input comes from above, falling slowly through kilometers of water. Dead plankton, fragments of organic matter, fecal pellets, and the remains of surface organisms drift downward in a steady but thin rain. By the time this material reaches the deepest trench, it has been stripped of much of its nutritional value. What remains is sparse, irregular, and unpredictable. Organisms living here must survive long periods with very little food. Growth is slow, reproduction is infrequent, metabolism is tuned toward conservation rather than expansion. This is not an environment that rewards speed or abundance. It rewards efficiency. Some life forms supplement this limited supply with chemical energy. Certain bacteria can metabolize compounds like methane, hydrogen sulfide, or ammonia, deriving energy from chemical reactions rather than sunlight. These processes, known as chemosynthesis, form the base of some deep-sea food webs. However, in Challenger Deep, such systems are not widespread. Life here is more diffuse, more isolated. What surprises scientists is not just that life exists, but that it exhibits complexity. Multicellular organisms have been observed. Crustaceans, worms, and other invertebrates inhabit the trench floor. These are not simple, primitive life forms clinging to existence. They are specialized, adapted, and integrated into functioning ecosystems, however sparse those ecosystems may be. Pressure plays a defining role in shaping this life. At extreme depth, pressure affects the structure of proteins, the stability of cell membranes, and the behavior of enzymes. Surface organisms exposed to such pressure experience rapid failure at the molecular level. Proteins misfold, membranes lose integrity, metabolic pathways break down. Deep-sea organisms avoid this not through brute strength, but through chemistry. Their proteins are structured to remain stable under compression. Their membranes contain different lipid compositions that maintain flexibility and function despite pressure. Enzymes are adapted to operate efficiently in cold, high-pressure conditions where surface enzymes would become sluggish or inactive. These adaptations are not optional, they are fundamental. Without them, life cannot persist at these depths. Another unsettling aspect is how fragile these organisms appear when removed from their environment. Many deep-sea creatures look soft, gelatinous, or underdeveloped when brought to the surface. This has led to misconceptions about their robustness. In reality, these forms are optimized for uniform pressure. Remove that pressure too quickly, and tissues rupture, gases expand, and structures collapse. This fragility makes direct study difficult. Many organisms cannot survive decompression, meaning they can only be observed remotely or preserved in altered states. Scientists must infer function from structure, genetics, and behavior captured briefly on camera. Despite these limitations, genetic analysis has revealed surprising diversity. DNA extracted from deep-sea samples shows lineages that diverged long ago from their surface relatives. Evolution has had time to work here, slowly shaping organisms to fit conditions that have remained stable for millions of years. This stability is itself counterintuitive. While the surface world experiences constant change driven by weather, seasons, and climate, the deep ocean is remarkably consistent. Temperature varies little. Darkness is absolute. Pressure is constant. This creates an environment where evolutionary pressures are steady rather than fluctuating. As a result, adaptation here favours specialisation over flexibility. Organisms are finely tuned to a narrow range of conditions. They thrive where they are, but they cannot easily migrate or adapt to different environments. This isolation contributes to the uniqueness of deep-sea life. Another factor complicating understanding is scale. Populations are sparse. Encounters between organisms may be rare. Reproductive strategies differ from surface norms. Some species may reproduce infrequently, relying on long lifespans rather than rapid turnover. Others may release larvae that drift upward, spending part of their life cycle in shallower waters before returning to depth. These life histories are difficult to document. Observation windows are brief. Sample sizes are small. Many conclusions are drawn from limited data, making generalization risky. Even microbial life behaves differently at depth. Bacteria and archaea in extreme environments often have slow metabolic rates. They may take years to divide. They exist in states that blur the line between active life and dormancy. This challenges assumptions about what constitutes biological activity. The presence of life in Challenger Deep also raises uncomfortable questions about contamination. Human exploration introduces foreign materials, including microbes, into environments that have remained isolated for geological timescales. While the impact of such introductions is not fully understood, scientists are increasingly cautious about minimizing disturbance. Life here is not resilient in the way surface ecosystems are. Recovery from disruption may take centuries or longer. A single disturbance could have long-lasting effects. The existence of deep-sea life also forces a re-evaluation of Earth's habitable space. Most of the planet's biosphere by volume lies below the surface, in environments that receive no sunlight. This reframes the idea of habitability away from surface-centric models. Earth is not primarily a sunlit world with dark margins. It is a dark world with a thin illuminated layer. This perspective has implications beyond Earth. If life can exist and persist in places like Challenger Deep, then environments once dismissed as inhospitable elsewhere may warrant reconsideration. Subsurface oceans on icy moons, deep beneath layers of ice and rock, share some characteristics with Earth's deep trenches. Studying life here informs broader questions about biology in the universe. But even without looking outward, the implications for Earth science are profound. Life influences chemistry. It affects sediment composition. It participates in nutrient cycling, even at extreme depth. Ignoring these contributions would leave an incomplete picture of how the planet functions. For scientists, the discomfort comes from realizing that life does not conform neatly to expectations. It does not require comfort. It does not require abundance. It does not require light. Given enough time and stability, It finds ways to persist under conditions that feel fundamentally hostile. This persistence complicates exploration. Life must be considered not just as an object of study, but as an active component of the environment. Its presence influences measurements, its disturbance alters conditions, its resilience challenges assumptions. The phrase, "life that should not exist," reflects a failure of imagination rather than a biological truth. What Challenger Deep demonstrates is that the criteria used to judge habitability were incomplete. They were shaped by surface experience and limited observation. As machines continue to explore these depths, they encounter organisms that defy categorization. Some resemble known groups but behave differently. Others appear so rarely that classification remains tentative. Each encounter adds to a growing sense that the deep ocean is not a marginal environment, but a central one, operating according to rules that science is still learning to articulate. Life in Challenger Deep does not announce itself. It does not flourish visibly. It exists quietly, persistently, shaped by pressure, darkness, and scarcity. Its presence is not comforting. It is challenging. It forces scientists to confront the adaptability of biology and the limits of their own frameworks. And once life is acknowledged as a permanent feature of this environment, attention naturally turns to the forms it takes, to the creatures that move through this darkness, often unseen, often unnamed, and to the difficulty of understanding organisms that rarely reveal themselves fully to observation. In environments that are well lit, frequently visited and easily sampled, naming life feels almost automatic. A creature is seen, described, compared to known forms, placed into a category, and given a label that allows it to be discussed, studied, and remembered. Names give the impression of understanding. They suggest that something has been seen clearly enough to be fixed in language. In the deepest parts of the ocean, that process breaks down. At the bottom of Challenger Deep, many creatures exist without names, not because they are rare in the environment itself, but because they are rare to us. They appear briefly, partially, often at the edge of visibility, and then disappear back into darkness. What scientists encounter here is not a catalogue of species, but a series of fleeting impressions that resist classification. This creates a fundamental problem. Biology depends on observation. Observation depends on seeing. And seeing in this environment is compromised at every level. The first limitation is light. As already established, there is no ambient illumination at these depths. Every visual observation relies on artificial light sources carried by submersibles or remotely operated vehicles. These lights are narrow, directional, and finite. They illuminate only what they are pointed at, and only for as long as power allows. Outside that cone, everything remains invisible. This means that observation is not passive, it is intrusive. Turning on a light does not simply reveal an environment, it alters it. Some organisms retreat instantly from illumination. Others freeze. Some are attracted briefly, mistaking light for bioluminescent signals. The behaviour observed may not reflect normal behaviour at all. This complicates interpretation. When a shape moves across the camera's field of view, scientists must ask whether they are seeing a natural interaction or a reaction to the observing machine itself. There is no control condition. There is no unlit comparison. Visibility is further limited by distance. Even the most powerful lights scatter quickly in water filled with fine particles. Sediment stirred by a submersible's movement can obscure vision almost immediately. A single maneuver can reduce visibility to near zero for minutes or longer. As a result, observation windows are brief and unpredictable. Within those windows, scale becomes ambiguous. Without familiar reference points, it is difficult to judge size accurately. A small organism close to the camera may appear large. A larger organism farther away may appear small. Depth perception is unreliable. Shadows distort shape. This leads to misidentification. Early deep-sea footage often described creatures as monstrous or oversized. not because they were, but because scale cues were missing. Modern scientists are more cautious, but uncertainty remains. Then there is the issue of resolution. Cameras capable of withstanding extreme pressure must compromise between durability and sensitivity. High-resolution imaging is possible, but it comes at the cost of power and data storage. Many missions prioritize broader coverage over fine detail. As a result, organisms are often recorded as silhouettes, partial forms, or blurred shapes. From such data, classification is difficult. Traditional taxonomy relies on detailed morphological features, body symmetry, appendage structure, mouth parts, surface textures. These details are often invisible in deep-sea footage. Even when an organism is clearly present, critical features may be obscured. Sampling offers another route, but it introduces its own problems. Capturing organisms at extreme depth without damaging them is challenging. Nets and traps disturb fragile forms. Pressure changes during retrieval can destroy soft tissues. Many organisms arrive at the surface unrecognizable compared to their living state. This means that some of the creatures scientists know exist in Challenger Deep have never been seen intact in their natural form. They are known only from fragments, genetic traces, or degraded specimens. Naming such organisms feels premature, yet leaving them unnamed limits discussion. Genetic analysis has helped bridge this gap. Environmental DNA, or eDNA, allows scientists to detect the presence of organisms by analysing genetic material suspended in water or sediment. This reveals biodiversity that cameras and nets miss. However, genetic data alone does not provide a full picture. A sequence can indicate that an organism exists, but not what it looks like, how it behaves, or how it interacts with its environment. As a result, scientists sometimes know that something is there without knowing what it is in any meaningful sense. This inversion is unsettling. Presence precedes form. Existence precedes description. When organisms are observed visually, they often defy easy categorization. Some resemble known groups but exhibit unfamiliar proportions or behaviors. Others appear so distinct that placing them within existing taxonomic frameworks feels forced. Evolution at extreme depth has had millions of years to explore solutions that surface environments never acquired. Some creatures appear almost unfinished by surface standards. Bodies lack rigid skeletons. Appendages are reduced or elongated. Movement is slow, deliberate, and minimal. These forms make sense under constant pressure and low energy availability, but they look strange when viewed through a surface-biased lens. The scarcity of encounters adds another layer of difficulty. Many deep-sea organisms exist at low population densities. They may be widely spaced across the seafloor or water column. A single mission might encounter an organism once for a few seconds and never see it again. That is not enough to establish variability, life cycle, or behaviour. Without repeated observation, it is hard to know whether a recorded individual represents a common species or a rare outlier. Naming something based on a single encounter risks over-interpretation, but waiting for multiple encounters may mean waiting decades. This tension creates hesitation. Scientists are careful with names because names imply confidence. They suggest boundaries. In Challenger Deep, boundaries are blurred. Another complication is movement. Some deep-sea creatures are not tied to the seafloor. They drift, swim, or hover in the water column. Their vertical range may span hundreds or thousands of meters. A creature observed near the bottom may not belong exclusively to that depth. It may be passing through. This mobility complicates classification by habitat. It also complicates understanding of ecological roles. Is an organism a resident of the trench or a transient visitor? Does it feed locally or elsewhere? Without tracking over time, answers remain speculative. Bioluminescence adds further confusion. Many deep-sea organisms produce light, but this light is often brief, directional, and context-dependent. A camera may capture a flash without capturing the organism that produced it. Interpreting these signals requires inference. Is the light a defense mechanism, a mating signal, or an incidental chemical reaction? Without context, certainty is elusive. The problem of seeing clearly is not limited to visual clarity. It extends to conceptual clarity. Surface biology is built on assumptions shaped by abundant observation. Patterns emerge because data is plentiful. In Challenger Deep, data is sparse. Patterns are harder to detect. This scarcity encourages caution, but it also slows understanding. Hypotheses remain tentative. Conclusions are framed conservatively. Many organisms remain described in papers as unidentified or undescribed, sometimes for decades. There is also a human bias at work. Scientists are trained to recognize what they already know. In unfamiliar environments, this can lead to forcing new observations into existing categories. A strange crustacean may be described as a variant of a known group, even if it represents something more distinct. Over time, this can obscure genuine novelty. To counter this, deep-sea biologists increasingly rely on interdisciplinary approaches. Morphology is combined with genetics, chemistry, and environmental context. Even then, uncertainty remains. The naming problem has practical consequences. Conservation efforts depend on knowing what exists. Without names, organisms are harder to protect. Environmental impact assessments struggle to account for unknown species. Decisions about deep-sea mining, waste disposal, or exploration may proceed without full awareness of biological consequences. This is particularly concerning in extreme environments where recovery from disturbance is slow. If an organism is impacted before it is even recognized as distinct, the loss may go unnoticed. There is also an emotional dimension to unnamed life. Humans relate to the world through language. Names allow attachment. They allow stories. Unnamed creatures remain abstract, harder to care about, easier to overlook. This does not diminish their value, but it affects how they are perceived. Scientists working in Challenger Deep are aware of this. Many speak cautiously, emphasizing the limits of current knowledge rather than making bold claims. They understand that what they see is partial, filtered through technology and constrained by environment. The problem of seeing clearly is compounded by time. Observations are brief. Missions are infrequent. Funding cycles move faster than deep-sea research can comfortably support. Long-term studies are rare. Continuity is hard to maintain. Despite these challenges, progress is being made. New imaging technologies improve sensitivity. Autonomous vehicles expand coverage. Machine learning assists in pattern recognition. Over time, more creatures will be observed repeatedly, described more fully and named. But even as knowledge grows, it is unlikely that clarity will ever be complete. Challenger Deep is not an environment that reveals itself easily. It does not present its inhabitants for inspection. It offers glimpses, not panoramas. This persistent partiality is what unsettles scientists, not the presence of strange creatures, but the inability to see them fully, consistently, or on demand. The realization that even with advanced technology, some aspects of life remain just beyond reach. Creatures without names are not failures of science. They are reminders of its boundaries. They indicate places where observation lags behind existence. They challenge the assumption that everything important can be categorized and labeled. As exploration continues, the hope is not to eliminate mystery but to narrow it responsibly. To acknowledge what is known, to admit what is not, and to proceed without pretending that clarity is guaranteed. And as attention shifts from individual organisms to the environment that shapes them, another question emerges. What kind of chemistry governs a place where pressure, darkness, and isolation alter not just biology, but the very reactions that make life possible? Chemistry behaves politely at the surface. Reactions follow expectations. Temperature, pressure, and concentration interact in ways that are predictable, repeatable, and well described by models refined over centuries. Even when reactions are complex, they unfold within ranges humans are comfortable working with. Change the temperature, adjust the pressure slightly, add a catalyst, and the outcome shifts in understandable ways. In the Hadal zone, chemistry does not behave politely. At the depth surrounding Challenger Deep, chemical reactions occur under conditions so far removed from the surface world that many of the assumptions built into classical chemistry begin to bend. Pressure is not a modifier here. It is a dominant force. Temperature is stable but cold. Sunlight is absent. Biological activity is sparse and uneven. The result is a chemical environment that feels familiar only in fragments. One of the first misconceptions scientists had to abandon was the idea that deep ocean chemistry is slow simply because it is cold. Temperature does influence reaction rates, but pressure alters reaction pathways in ways that temperature alone cannot explain. At extreme depth, molecules are forced into closer proximity. Volumes shrink. Bonds behave differently. Reactions that are unlikely at the surface can become favoured. Water itself changes character under immense pressure. Although it remains liquid, its density increases slightly, and its ability to dissolve substances changes. Gases behave differently. Carbon dioxide, methane, and nitrogen dissolve more readily, altering acidity and redox conditions. This means that the chemical backdrop against which life operates is not just colder and darker, but fundamentally rebalanced. One of the most striking features of Hadal chemistry is how oxygen behaves. Near the surface, oxygen distribution is shaped by photosynthesis, mixing, and atmospheric exchange. At extreme depth, oxygen arrives only through slow circulation from above. It is not replenished locally. Yet measurements in some trench environments reveal oxygen levels that are higher than expected. This initially puzzled scientists. In theory, oxygen should be depleted by microbial activity and slow circulation. In practice, the steep walls of trenches funnel cold, oxygen-rich water downward during certain circulation events. This creates pockets where oxygen persists longer than models predict. These oxygen anomalies affect everything else. Microbial metabolism shifts. Oxidation reactions proceed differently. Chemical gradients become sharper. The environment becomes patchy rather than uniform. Another surprising feature is the accumulation of organic carbon. While food input from above is limited, trenches act as collection points. Their shape funnels sinking material into confined areas. Over time, organic matter accumulates in sediments at higher concentrations than on surrounding abyssal plains. This creates chemical hotspots. Microbes break down organic material, consuming oxygen and producing byproducts like carbon dioxide, methane, and reduced sulfur compounds. These processes occur slowly but persistently. The result is a sediment chemistry that can differ dramatically from the overlying water. Pressure influences these processes by stabilizing certain intermediates and suppressing others. Reactions that would release gas at the surface remain dissolved at depth. This alters PAG and redox balance. Small changes in pressure or temperature can tip the system from one dominant pathway to another. Nitrogen cycling is also altered. Nitrification and denitrification, processes that convert nitrogen between different chemical forms, depend on oxygen availability and microbial activity. In the Hadal zone, these processes occur under conditions rarely studied elsewhere. Pressure-sensitive enzymes behave differently. Reaction rates shift. Some pathways become more efficient, others stall. Sulfur chemistry adds another layer of complexity. Sulfate is abundant in seawater, and under low oxygen conditions, microbes can use it as an electron acceptor, producing hydrogen sulfide. At the surface, this process is often associated with obvious smells and blackened sediments. At depth, hydrogen sulfide remains dissolved and chemically active, participating in further reactions rather than escaping. These reduced sulfur compounds interact with metals in the sediment, forming complex mineral assemblages. Iron, manganese, and other trace metals cycle between oxidation states. These cycles influence nutrient availability and microbial community structure. Pressure also affects mineral stability. Certain minerals that are unstable at the surface become stable at depth. Clay minerals compact and reorganize. Pore spaces shrink, trapping fluids under pressure. These fluids can become chemically distinct from surrounding seawater, enriched in dissolved elements and reduced compounds. When tectonic activity disturbs these sediments, trapped fluids can be released suddenly. This creates transient chemical anomalies. A localized pulse of methane, sulfide, or metal-rich fluid can alter conditions abruptly. For organisms adapted to long-term stability, these events represent rare but significant disruptions. From a scientific perspective, capturing these events is extremely difficult. They are unpredictable and short-lived. Instruments must already be in place, functioning properly, and capable of detecting subtle changes under extreme pressure. Another unsettling aspect of Hadal chemistry is contamination. Human-made compounds have been detected even at the deepest points. Persistent organic pollutants, microplastics, and industrial chemicals have been found in trench sediments and organisms. These compounds arrive through sinking debris and long-range transport, demonstrating that no part of the ocean is truly isolated. Chemically, this introduces new variables. Synthetic compounds interact with natural systems in unpredictable ways. They may persist longer at depth due to low temperatures and limited microbial degradation. Their long-term effects on deep-sea ecosystems remain poorly understood. For scientists, this is troubling. The Hadal zone was once thought to be buffered from surface activity by sheer depth. Chemistry tells a different story. The trench is connected to the rest of the ocean through slow but relentless processes. What happens at the surface eventually leaves a chemical signature even here. Pressure complicates detection of these compounds. Analytical techniques must account for changes that occur during sample retrieval. Gases may come out of solution. Reactions may proceed differently as pressure decreases. Preserving the original chemical state of a sample is extremely challenging. This means that much of what is known about Hadal chemistry is inferred rather than observed directly. Scientists rely on models constrained by limited data points. Each new measurement can force revisions. The interaction between chemistry and biology further complicates matters. Microorganisms do not just respond to chemistry, they shape it. Their metabolic processes alter pH, redox conditions, and nutrient availability. In turn, chemistry constrains which microbes can survive and how active they can be. This feedback loop operates slowly but persistently. Over long time scales, it influences sediment composition, fluid chemistry, and even the physical properties of the seafloor. The trench is not chemically inert. It is a living system, albeit one that operates on timescales and under conditions that challenge observation. Another factor that unsettles scientists is how sensitive these systems can be to disturbance. Because reaction rates are slow and conditions stable, recovery from disruption is prolonged. A chemical imbalance introduced by natural events or human activity may persist for decades or longer. This fragility contrasts with the apparent harshness of the environment. It is easy to assume that a place so extreme must be resilient. In reality, it is often the opposite. Stability allows specialization, but specialization reduces flexibility. The Hadal zone also challenges assumptions about equilibrium. Surface chemistry often approaches steady states due to rapid mixing and active cycling. At depth, isolation allows local conditions to persist. Pockets of unusual chemistry can exist side by side, separated by subtle gradients. Mapping these gradients is difficult. Sampling resolution is coarse. Instruments are few. Data coverage is sparse. Scientists must piece together a picture from fragments, aware that unseen variability may be significant. Pressure further complicates interpretation by affecting chemical equilibria directly. equilibrium constants measured at surface pressure do not apply. Laboratory experiments must be conducted under high-pressure conditions to replicate deep-sea chemistry accurately. Such experiments are expensive and technically demanding. As a result, many chemical processes in the Hadal zone remain only partially characterized. Models are provisional. Predictions carry wide uncertainty. This uncertainty is not a failure of science, but a reflection of the environment's complexity. What makes this chemistry particularly unsettling is that it operates largely out of sight, yet influences broader systems. Trenches play a role in carbon sequestration, nutrient cycling, and long-term climate regulation. Ignoring their chemistry would leave gaps in understanding how Earth functions as an integrated system. The Hadal zone forces scientists to confront the idea that extreme environments are not peripheral. They are integral. Their chemistry matters not despite their isolation, but because of it. As exploration continues, chemical sensors become more sensitive, sampling techniques improve, models refine. But each advance reveals new complexity rather than closure. This is a recurring theme in Challenger Deep research. Answers generate new questions. Clarity exposes additional layers of uncertainty. Chemistry, like biology and physics here, resists simplification, and once chemistry is recognized as active, dynamic, and deeply intertwined with geology, attention turns naturally to the physical instability of the environment itself. Because beneath the chemical gradients and biological adaptations lies a seafloor that is never truly at rest, shaped by forces that operate silently but continuously beneath the deepest water on Earth. The bottom of the ocean is often imagined as a quiet place, still and settled, where sediment drifts down gently and accumulates undisturbed over long periods of time. That image holds in some parts of the deep sea, but it fails completely in the region surrounding Challenger Deep. Here the seafloor is not a passive surface. It is an active boundary shaped by constant stress, sudden movement, and forces that operate whether anyone is there to observe them or not. Challenger Deep sits along one of the most dynamic tectonic zones on the planet. It exists because the Pacific Plate is sliding beneath the Mariana Plate in a process known as subduction. This movement is slow when measured year to year, only a few centimeters annually, but over geological time it is relentless. The plate does not glide smoothly. It locks, strains, and then releases energy abruptly. That release is what humans experience as earthquakes. At extreme depth, these earthquakes behave differently than they do near the surface. The pressures involved are immense, and the materials under stress respond in ways that are still not fully understood. Faults may slip silently or rupture violently. Energy can be absorbed, redirected, or focused depending on the structure of the crust and the composition of sediments. This makes the trench a place of constant tension. Even when nothing appears to be happening, stress is accumulating, the seafloor is not resting, it is waiting. Earthquakes in this region do not always announce themselves clearly. Some are too deep to produce strong surface shaking. Others generate seismic waves that travel vast distances through the Earth before being detected. In some cases, movement occurs slowly enough to avoid producing a classic earthquake at all, instead releasing energy through gradual deformation. These slow slip events are particularly unsettling for scientists because they are difficult to detect and poorly constrained. They may reshape parts of the seafloor without obvious warning. Instruments deployed on the bottom may record subtle shifts in pressure, orientation, or chemical gradients without an immediately obvious cause. When energy is released more suddenly, the effects can be dramatic. Earthquakes can trigger underwater landslides along the steep walls of the trench. These slopes are among the steepest on Earth, in some places dropping thousands of meters over relatively short horizontal distances. Sediments here are compacted by pressure but not cemented into solid rock. They exist in a precarious state, stable only until disturbed. When a slope fails, sediment can move rapidly downslope in dense flows. These underwater landslides do not behave like avalanches on land. They are heavy, fluidized masses that can travel long distances along the trench floor, reshaping the landscape as they go. They bury existing features, expose new surfaces, and alter chemical conditions in their wake. For any instrument or organism in their path, these events are catastrophic. The frequency of such landslides is difficult to estimate. Direct observation is rare. Most evidence comes from sediment cores that reveal layers of disrupted material, or from sonar mapping that shows scars along trench walls. These records suggest that landslides occur repeatedly over geological time, triggered by earthquakes both local and distant. Even earthquakes occurring hundreds of kilometers away can send seismic waves through the region, destabilizing slopes that are already near their threshold. This means that the seafloor can change suddenly without a nearby epicenter. From a scientific perspective, this instability complicates everything. Measurements taken at one time may not be valid later. A sampling site chosen carefully based on previous mapping may be buried or altered by the time a follow-up mission arrives. Long-term monitoring becomes difficult when the ground itself is mobile. This mobility also affects biology. Organisms living on or within sediments must contend with periodic disturbance. Some may be buried, others may be displaced. Over time, this selects for life strategies that tolerate disruption. Burrowing organisms, slow-growing communities, and species capable of recolonizing disturbed areas have an advantage. But even these adaptations have limits. A sufficiently large landslide can reset an area completely, erasing biological communities and chemical gradients that took centuries to develop. The seafloor's restlessness is not limited to dramatic events. There is constant low-level movement as well. Sediments compact slowly under pressure. Fluids trapped within pore spaces migrate. Chemical reactions alter mineral structures. The ground shifts imperceptibly but continuously. This slow motion matters. It influences how pressure is distributed, how fluids move, and how stresses accumulate. Over time, these small changes can set the stage for larger events. The system is interconnected. Nothing happens in isolation. Another factor that unsettles scientists is the vertical extent of seismic activity in this region. Some earthquakes occur at depths that challenge existing models of how rocks behave under pressure and temperature. At such depths, rocks are expected to deform plastically rather than fracture. Yet seismic signals indicate brittle failure. This contradiction points to gaps in understanding. It suggests that water, pressure, and mineral composition interact in ways that allow unexpected behavior. Studying these processes requires data from exactly the kinds of environments that are hardest to access. The trench also plays a role in tsunami generation. Large earthquakes along subduction zones can displace massive volumes of water, sending waves across entire ocean basins. While Challenger Deep itself is far from many coastlines, the processes occurring there are part of the broader system that produces these hazards. Understanding how energy is transferred through the trench, how sediment movement contributes to displacement, and how fault geometry affects wave propagation is essential for accurate hazard modelling. Yet much of this understanding depends on indirect inference rather than direct observation. For scientists working with deep-sea instruments, the moving seafloor presents practical challenges. Equipment deployed on the bottom must be designed to tolerate shifting ground. Anchors must accommodate movement. Sensors must remain functional even if partially buried or tilted. In some cases, instruments are lost entirely, not through failure, but through burial. A device deployed carefully may simply disappear beneath meters of sediment after a landslide. Recovery becomes impossible. Data streams end without explanation. This unpredictability makes planning difficult. Missions must accept a certain rate of loss. Redundancy becomes necessary. Data gaps are expected rather than exceptional. The idea of a seafloor that never truly rests also complicates interpretation of chemical and biological data. Changes observed over time may reflect environmental shifts rather than experimental error. Distinguishing between these possibilities requires careful correlation across multiple data sources. For example, a sudden change in oxygen concentration might indicate altered circulation, increased microbial activity, or sediment disturbance from a landslide. Without direct observation of the event, scientists must reconstruct the cause from incomplete evidence. This reconstructive process is intellectually demanding and emotionally humbling. It requires accepting uncertainty and resisting the urge to oversimplify. The trench does not provide clean narratives, it provides fragments. The constant motion also reinforces the sense that Challenger Deep is not an isolated pit, but part of an active system. Forces originating deep within the Earth express themselves here. Energy moves upward, outward, and laterally. The trench is both a receiver and a transmitter of geological processes. This interconnectedness challenges surface-centric views of Earth dynamics. It highlights the importance of deep environments in shaping planetary behaviour. What happens kilometres below the ocean's surface influences phenomena experienced far above it. The unsettling aspect is not just that the seafloor moves, but that it moves largely unseen. Changes occur without witnesses. Events unfold beyond the reach of cameras and sensors. By the time evidence is collected, the moment has passed. Scientists are accustomed to studying change, but they prefer to observe it directly. Challenger Deep denies that comfort. It forces reliance on aftermaths rather than events, on traces rather than experiences. This is part of why the environment resists full understanding. It does not pause for measurement. It does not wait for instruments to be in place. It operates continuously, indifferent to observation. As exploration continues, researchers develop new methods to infer activity. Seismic networks improve, long-term monitoring becomes more robust, models grow more sophisticated. But the fundamental reality remains. The seafloor beneath Challenger Deep is alive with motion. This realization shifts attention from static descriptions to dynamic processes. It encourages scientists to think in terms of flux rather than structure, change rather than stability. The trench is not defined solely by how deep it is, but by how it moves. And once movement is acknowledged as constant, another question follows naturally. If the seafloor is active, reshaping itself through earthquakes and landslides, then how does this motion interact with the broader environment above it, turning what might seem like an isolated abyss into a system that communicates with the rest of the ocean in subtle but consequential ways? It is tempting to think of the deepest part of the ocean as a kind of final resting place, a basin where things fall, settle, and remain undisturbed. The image is intuitive. Gravity pulls material downward. Depth suggests stillness. Darkness implies silence. From the surface, Challenger Deep can seem like the end of the line, a place where motion stops and history accumulates layer by layer. That image is misleading. Challenger Deep is not a quiet grave. It is not a static pit collecting debris in eternal darkness. It is a moving system, shaped continuously by forces that link it to the rest of the planet. What makes it unsettling to scientists is not just how deep it is, but how active it remains despite that depth. The first sign that this environment is dynamic rather than dormant comes from circulation. Even at extreme depth, the ocean is not still. Water masses move slowly but persistently, driven by differences in temperature, salinity and density that originate far from the trench itself. Cold, dense water formed near the poles sinks and travels along the seafloor, eventually reaching the deepest basins. This movement is not fast, but it is steady, and it connects Challenger Deep to global ocean circulation. These deep currents influence everything. They transport oxygen, nutrients and chemical signatures from distant regions. They shape sediment deposition patterns. They affect temperature stability. The bottom of the trench is not isolated from the rest of the ocean. It is integrated into it through motion that is easy to overlook because it operates on long timescales. This circulation means that Challenger Deep is constantly exchanging material with its surroundings. Water does not simply arrive and remain. It flows through, carrying dissolved gases, organic compounds, and suspended particles. Over time, this exchange prevents the trench from becoming chemically stagnant. Sediment movement adds another layer of activity. Material does not fall evenly into the trench and settle gently. The steep walls funnel debris downward in irregular pulses. Landslides triggered by earthquakes or gradual slope failure deliver large amounts of sediment in short periods. Between these events, finer particles continue to drift down from above. Once sediment reaches the bottom, it does not remain inert. Under immense pressure, sediments compact and expel fluids. These fluids migrate through pore spaces, carrying dissolved chemicals with them. Over time, this creates vertical and horizontal gradients in chemistry that are constantly evolving. This slow fluid movement is invisible to the eye, but its effects are measurable. Changes in pore water chemistry influence microbial activity. They alter mineral stability. They affect how elements like carbon, nitrogen, and sulfur are stored and released. The seafloor is not a passive archive, it is an active reactor. Biology participates in this system as well. Microorganisms living within sediments consume organic matter and alter chemical conditions as they do so. Their activity may be slow, but it is persistent. Over long periods, microbial metabolism reshapes the chemical landscape of the trench floor. Even larger organisms contribute. Burrowing, feeding, and movement disturb sediments locally. These disturbances may seem insignificant in isolation, but over time they influence how material is mixed and redistributed. Life, even when sparse, leaves an imprint. The idea of the trench as a grave also overlooks its connection to the Earth's interior. Challenger Deep exists because of subduction, a process that continuously recycles crust into the mantle. This movement does not stop at the surface. It continues beneath the seafloor, shaping pressure, temperature, and stress conditions. Fluids released from the subducting plate migrate upward through the overlying crust. These fluids carry heat and chemicals that influence the trench environment. In some cases, they alter sediment chemistry. In others, they contribute to the formation of the mineral deposits. This upward movement links deep geological processes directly to the seafloor. Seismic activity reinforces this connection. Earthquakes do not just reshape the trench walls. They alter fluid pathways, trigger chemical reactions, and redistribute sediments. An earthquake can change conditions across a wide area in a matter of seconds, followed by years of gradual adjustment. For scientists, this means that Challenger Deep must be understood as a system in flux rather than a fixed location. Measurements taken at one time represent a snapshot, not a permanent state. Conditions observed today may not persist tomorrow, even if changes occur slowly. This challenges certain assumptions about deep-sea stability. While temperature and darkness are constant, other variables are not. Oxygen levels can shift with circulation changes. Chemical gradients can evolve as sediments compact or fluids migrate. Biological communities may respond to these shifts in ways that are not immediately obvious. The moving nature of the system also complicates long-term studies. Instruments deployed on the seafloor may record gradual trends or sudden changes. Interpreting these signals requires distinguishing between local disturbances and broader system behaviour. Was a change caused by a landslide nearby, a shift in deep water circulation, or microbial activity within the sediment? Without direct observation of every contributing factor, certainty is difficult. Scientists must integrate data from multiple sources and scales. Seismology, chemistry, biology, and physical oceanography all intersect here. Understanding emerges slowly, through accumulation rather than revelation. Another reason the trench resists the label of grave is that it does not merely receive material, it also influences what happens above it. By funneling organic matter into confined areas, It affects how carbon is stored in the deep ocean. By participating in circulation, it influences nutrient distribution. By hosting unique biological communities, it contributes to global biodiversity. These contributions are subtle, but they matter. Ignoring the trench would leave gaps in models of ocean chemistry, carbon cycling, and even climate regulation. The deepest places are not marginal, they are integral components of Earth's systems. This reframing alters how scientists approach the environment. Instead of asking what has accumulated here, they ask how material moves through it. Instead of focusing on depth as an endpoint, they focus on processes that continue regardless of depth. The unsettling part is that many of these processes operate beyond direct human observation. They unfold slowly or intermittently. They leave traces rather than spectacles. This requires a shift in scientific mindset, away from event-driven narratives towards system-based thinking. It also demands patience. Changes may take years to detect. Patterns may only emerge after long-term monitoring. Funding cycles and mission planning must adapt to timescales that do not align neatly with human schedules. The notion of a moving system also highlights vulnerability. Because processes are slow, disturbances can have long-lasting effects. A chemical imbalance or physical disruption may persist for decades. Recovery is not guaranteed, and resilience cannot be assumed. This vulnerability contrasts sharply with the apparent harshness of the environment. It is easy to assume that an extreme place must be tough and self-correcting. In reality, stability has allowed specialization, and specialization reduces flexibility. Recognizing challenger. Deep as a moving system rather than a quiet grave changes how responsibility is framed. Exploration is not just observation, it is interaction. Even minimal disturbance can alter trajectories that take years to unfold. For scientists, this realization reinforces caution. It encourages restraint. It underscores the importance of designing missions that minimize impact and maximize understanding. As attention continues to shift from static descriptions to dynamic relationships, the focus naturally turns toward humanity's own role in this system. Because once Challenger Deep is understood as active and connected, the question is no longer whether humans can reach it, but what happens when they do, and what the cost of that presence truly is. Human presence at the deepest point on Earth has always been brief, deliberate, and uneasy. There has never been a sense that people belong there, only that they can pass through under very specific conditions for very short periods of time if everything works exactly as planned. The bottom of the ocean does not welcome human visitors. It tolerates them, temporarily, and that distinction matters. When humans first reached Challenger Deep, the achievement was framed as a triumph of engineering and determination. And in many ways, it was. Reaching such depth required overcoming immense technical challenges, from pressure-resistant hulls to reliable life support systems, and navigation in complete darkness. But beneath the celebration lay a quieter truth. Every human descent to the bottom of the trench has carried a cost that goes far beyond funding, logistics, or headlines. The most obvious cost is risk. At extreme depth, risk is not abstract. It is immediate and absolute. Unlike many surface expeditions, there is no margin for improvisation. If something fails, there is no rescue coming from below. The only possible direction of escape is upward, and ascent depends entirely on systems functioning as designed. Human bodies cannot tolerate pressure changes, cold, or darkness without protection. The submersible is not just a vehicle. It is a fragile island of survivability in an environment that allows no mistakes. This reality shapes every decision. Descent profiles are conservative. Time spent at the bottom is limited. Movements are slow and calculated. There is no wandering, no curiosity-driven detours. Presence is purposeful, because lingering increases exposure to risk. Even then, the psychological weight of being there is significant. Inside a submersible, the environment feels controlled. but the knowledge of what exists just outside the hull never fully recedes. Pressure is invisible, but it is always present. Darkness is total beyond the reach of artificial light. Communication delays remind occupants that they are alone in a way few environments can replicate. For many who have made the descent, the experience is described not as fear, but as vigilance. Attention narrows, awareness sharpens, every sound, every vibration, every data readout matters. This level of focus is exhausting. Human presence at the bottom is not just physically demanding, it is mentally taxing. The cost also includes technological strain. Crude submersibles capable of reaching such depths are rare, expensive, and difficult to maintain. Each dive places stress on materials that cannot be fully reversed. Hulls experience compression cycles that degrade structural integrity over time. Systems must be inspected meticulously after every mission. The number of safe descents is finite. This limits how often humans can go. Unlike robotic systems, which can be replaced or redesigned more easily, human-rated vehicles carry a higher standard of safety. That standard comes with constraints, fewer missions, higher costs, longer preparation times. Because of this, human presence at the bottom is often symbolic rather than practical. People go down to demonstrate feasibility, to observe directly, to validate instruments, or to make targeted observations that benefit from human judgment. But sustained exploration is left to machines. This division reflects an uncomfortable truth. Humans are not well suited to this environment. We can visit, but we cannot stay. Every moment at depth is borrowed time. There is also an environmental cost to consider. Even the most carefully planned human missions disturb the environment they enter. Thrusters stir sediment. Lights alter behaviour. Sampling removes material that may take centuries to replace. While the scale of disturbance is small compared to industrial activity elsewhere, its impact in such a slow-moving system can be disproportionate. Scientists are acutely aware of this. Deep-sea environments recover slowly. Biological processes operate on long timescales. A single disturbance may persist far longer than it would in shallower waters. Human presence, even when cautious, is not neutral. This raises ethical questions that are still being debated. Is the knowledge gained worth the disturbance caused? How much impact is acceptable in an environment that is both fragile and poorly understood? These questions do not have simple answers. The cost of going there also includes opportunity cost. Resources devoted to extreme depth exploration are resources not used elsewhere. Research vessels, funding, and personnel are finite. Deciding to send a mission to challenge a deep means deciding not to send missions to other regions that may also hold important clues about Earth systems. This trade-off is particularly stark because data returned from extreme depth missions is often limited. A single descent may produce only hours of observation. Instruments may fail, samples may be lost. The risk-to-reward ratio is high and not always predictable. Yet scientists continue to justify these missions, not because they are efficient, but because some questions cannot be answered any other way. Direct human observation provides context that instruments alone sometimes cannot. The ability to interpret unexpected situations in real time has value. Still, even this value is weighed carefully. Human presence is increasingly seen as supplementary rather than central. The trend is toward fewer crewed descents and more reliance on autonomous and remotely operated systems. Another cost is psychological distance from the public. Crewed missions to space capture imagination because people can relate to the sky. The ocean depths lack that familiarity. Human presence there does not resonate as strongly with shared cultural narratives. This affects public support and funding priorities. As a result, deep-sea exploration often operates quietly, without the sustained attention given to space missions. Scientists working in this field are accustomed to explaining why their work matters, why it is worth the risk, and why the deepest places on Earth deserve study. The cost of going there also includes uncertainty. Every human descent is, in some sense, experimental. Conditions can change. Equipment can behave unexpectedly. The environment may reveal features that were not anticipated. Planning reduces uncertainty, but it cannot eliminate it. This uncertainty demands humility. Scientists must accept that some missions will fail, that some data will be ambiguous, and that some questions will remain unanswered. Human presence does not guarantee clarity. There is also a personal cost. Those who participate in such missions carry the experience with them long after the ascent. The memory of isolation, darkness, and vulnerability leaves an imprint. For some, it deepens appreciation for Earth's complexity. For others, it reinforces a sense of human limitation. These experiences shape how scientists talk about the deep ocean. The language is often cautious, respectful, and measured. There is little bravado. Success is defined not by conquest, but by safe return and incremental understanding. From a broader perspective, human presence at the bottom forces a reckoning with motivation. Why go there at all? What drives people to enter an environment that offers no comfort, no immediate reward, and no guarantee of success? Part of the answer lies in curiosity. Part lies in responsibility. The deep ocean plays a role in global systems that affect climate, geology, and life as a whole. Ignoring it would leave critical gaps in understanding, but curiosity and responsibility do not erase cost, they contextualize it. As technology advances, the balance continues to shift. Improved robotics reduce the need for human presence. Sensors become more capable. Data transmission improves. Over time, the role of humans at extreme depth may become increasingly rare, reserved for moments when direct observation is uniquely valuable. This shift reflects an acceptance of limits. Humans do not need to be everywhere to understand everything. Some environments are better approached indirectly. The cost of going there, then, is not just financial or physical, it is philosophical. It forces a reconsideration of how exploration should be conducted, where humans belong, and when restraint is wiser than presence. Challenger Deep does not demand human visitation to exist or to function. It existed long before anyone reached it, and it will continue long after. Human presence adds knowledge, but it also adds impact. Balancing these realities is an ongoing challenge, as scientists continue to weigh the value of human descent against its costs. Attention turns increasingly toward what can be learned without going there personally. Toward data collected over long periods, patterns observed indirectly, and signals detected remotely. Because if the deepest place on Earth teaches anything clearly, it is that understanding does not always require presence, and that sometimes the most responsible way to explore is to step back and listen carefully to what the environment reveals on its own. Sound behaves honestly at the surface. It travels through air in predictable ways, fades with distance, reflects off solid objects, and arrives at the ear with cues that help the brain reconstruct space. We know instinctively where a sound comes from, how far away it is, and whether it represents something familiar or threatening. This intuitive relationship collapses in the deepest parts of the ocean, where sound becomes the primary sense, but behaves in ways that resist interpretation. At depths surrounding Challenger Deep, sound does not merely travel differently. It occupies a different role altogether. It replaces vision, replaces proximity, and replaces certainty. Scientists rely on it because they must, not because it is reliable in the way light is at the surface. And the data it produces is often unsettling, not because it is dramatic, but because it is ambiguous. Water carries sound far more efficiently than air. At depth, sound waves travel faster and over longer distances, bending as they move through layers of varying temperature, pressure, and density. This creates an environment where a sound generated far away can arrive unexpectedly, distorted but still detectable. Direction becomes difficult to determine. Distance becomes uncertain. A low-frequency signal might originate nearby or hundreds of kilometers away. This uncertainty is not a minor inconvenience. It shapes how scientists interpret nearly everything they hear. Hydrophones deployed in deep trenches record a constant background of sound. Some of it is expected. Distant earthquakes generate low-frequency rumblings that pass through the earth and into the water column. Ice cracking in polar regions produces signals that propagate astonishing distances. Even storms at the surface leave acoustic fingerprints detectable far below. But mixed into this background are signals that are harder to explain. Some are transient, appearing briefly and then disappearing. Others repeat irregularly. Some change subtly over time. They do not match known seismic patterns. They do not correspond clearly to biological activity. They do not align neatly with human-generated noise. These signals are not dramatic. They are not loud. They are simply there, recorded faithfully by instruments that have no interpretation built into them. Making sense of them requires context that is often missing. One source of confusion is the way sound refracts at depth. Pressure increases sound speed, while temperature decreases it. Salinity adds another variable. The result is a complex acoustic landscape where sound waves curve rather than travel straight. A signal can arrive from below, above, or the side, regardless of where it originated. This makes localization difficult. A hydrophone may detect a signal, but be unable to determine its source with confidence. Triangulation requires multiple instruments spread over large areas, which is rarely feasible at extreme depth. As a result, many recordings remain spatially ambiguous. Another complication is the seafloor itself. The trench floor is uneven, layered with sediments of varying density. Sound interacts with these layers, reflecting, absorbing, and scattering. Some frequencies penetrate sediment and reflect back altered. Others are dampened completely. This interaction can produce echoes that resemble new signals. Distinguishing between original sounds and their reflections is not always straightforward. Models help, but models rely on assumptions about sediment composition and structure that may not be accurate everywhere. Biological sounds add another layer of complexity. Many deep-sea organisms are thought to be relatively quiet compared to their surface counterparts, but this assumption is increasingly questioned. Some organisms may produce sounds for communication, navigation, or defense. Others may generate noise incidentally through movement or interaction with sediment. These sounds are often subtle and low frequency. They may overlap with geological signals. Without direct observation, attributing a sound to a biological source remains speculative. There have been recordings of rhythmic patterns that suggest life, but without visual confirmation, certainty remains elusive. Scientists must weigh multiple interpretations and resist the temptation to assign meaning prematurely. Human-generated noise also reaches the deep ocean. Shipping traffic, sonar use, and industrial activity introduce sounds that propagate far beyond their point of origin. Even at extreme depth, traces of surface activity can be detected. This complicates baseline measurements. What sounds natural and what sounds artificial may overlap. Long-term acoustic monitoring reveals trends that are difficult to explain. Changes in background noise levels over time suggest shifts in surface activity, circulation patterns, or environmental conditions. Disentangling these influences requires integrating data from multiple disciplines. Signals related to seismic activity are particularly important and particularly challenging. Earthquakes generate a range of acoustic signatures, some travelling through rock, others through water. The trench environment modifies these signals in ways that are still being studied. In some cases, hydrophones detect precursory signals before major seismic events. In others, they record aftershocks that appear decoupled from known fault activity. These observations raise questions about how stress is distributed and released in subduction zones. The uneasy part is not that scientists lack explanations, it is that multiple explanations remain plausible. Data does not point cleanly in one direction. Instead, it suggests overlapping processes interacting in complex ways. Pressure also affects sound generation itself. Materials under stress may produce acoustic emissions as they deform or fracture. Sediments compacting under pressure may release sounds too subtle to be felt but detectable by sensitive instruments. These emissions blur the line between geological and acoustic processes. Over time, patterns emerge, but they are statistical rather than definitive. A certain type of signal may correlate with known events more often than not. Confidence builds slowly. But absolute certainty remains rare. This uncertainty has practical implications. Acoustic data is used to infer processes that cannot be observed directly. Misinterpretation could lead to incorrect conclusions about seismic risk, sediment stability, or biological activity. Scientists respond to this by being cautious. Data is cross-referenced. Hypotheses are framed tentatively. Peer review is rigorous. But the discomfort remains. Sound, the most reliable sense in this environment, refuses to provide clear answers. There is also the issue of silence. Periods of relative quiet occur where expected signals are absent. This absence can be as puzzling as unexpected noise. Does it indicate a change in circulation, a lull in seismic activity, instrument malfunction? Without redundancy, interpretation is difficult. Instruments themselves contribute to uncertainty. Hydrophones must withstand pressure for long periods. Sensitivity can drift. Calibration can change subtly. Distinguishing environmental change from instrument change requires careful analysis. This is why acoustic datasets from the Hadal zone are often revisited years later, reanalyzed with improved models and broader context. Meaning evolves over time as understanding deepens. The emotional response to this kind of data is understated but real. Scientists are trained to seek clarity. Ambiguity is tolerated, but persistent ambiguity challenges confidence. When signals resist interpretation, they highlight the limits of current understanding. This does not lead to sensational conclusions. It leads to restraint. Claims are narrow. Language is careful. Papers emphasize uncertainty as much as findings. The uneasy nature of the data also influences funding and research priorities. Acoustic monitoring is expensive and logistically challenging. Deploying instruments at extreme depth requires significant investment. Deciding where to place them and for how long involves trade-offs. Despite these challenges, sound remains indispensable. It is the only sense that operates effectively over large distances at depth. Without it, many processes would remain completely hidden. As technology improves, resolution increases. New signal processing techniques extract more information from existing recordings. Machine learning assists in pattern recognition. Over time, some ambiguities resolve, but new ones emerge. This is the pattern Challenger Deep imposes. Each layer of understanding reveals further complexity. Each dataset answers some questions while raising others. The uneasy data does not point toward danger or mystery in a dramatic sense. It points toward a system that operates continuously, quietly, and largely beyond human perception. Sound offers glimpses into that system, but not a full picture. And as scientists continue to listen, to pass signals and silence alike, they are reminded that interpretation is always provisional. The environment does not explain itself. It must be inferred, cautiously, from incomplete evidence. This reliance on indirect sensing reinforces a broader theme. Challenger Deep is not a place that yields understanding through presence alone. It communicates through traces, patterns, and signals that require patience to decode. As attention shifts from sound to the meaning embedded in these signals, the focus naturally turns toward what Challenger Deep reveals about Earth as a whole. Because the data gathered here does not just describe a single location, it informs how scientists understand the planet's structure, behaviour, and limits in ways that extend far beyond the deepest trench. When scientists talk about Challenger Deep, they are rarely talking only about a location. They are talking about Earth in a stripped-down state, a version of the planet where familiar surface influences fall away and underlying processes become more visible. The deepest point on Earth functions less like an isolated curiosity and more like a diagnostic window. It reveals how the planet behaves when light, warmth, and human-scale intuition are removed from the equation. One of the first lessons Challenger Deep teaches is that Earth is not defined by its surface. The landscapes people inhabit, the climates they experience, and the ecosystems they see represent a thin outer layer. Beneath that layer lies a vastly larger environment governed by pressure, darkness, and slow-moving forces. Challenger Deep exists as proof that the surface is not the default state of the planet, but an exception. This reframing has consequences. Many models of Earth systems have historically emphasized surface processes because they are easiest to observe. Weather, erosion, biological productivity, and human activity dominate discussion. Challenger Deep reminds scientists that these processes sit atop a deeper framework that operates continuously, regardless of what happens above. Geologically, the trench exposes the mechanics of plate tectonics in a way few other places can. Subduction is not an abstract concept here, it is physically present. One tectonic plate is being forced beneath another, reshaping the planet from the inside out. This process recycles crust, generates earthquakes, and influences volcanic activity across entire regions. Studying Challenger Deep helps scientists understand how stress accumulates and is released within Earth's crust under extreme pressure. It challenges assumptions about rock behavior, fault mechanics, and energy transfer. Observations from this environment feed into broader models used to assess seismic risk in populated regions far from the trench itself. The lesson is uncomfortable but clear. What happens deep beneath the ocean floor affects what happens on land. Earth is not compartmentalized. It is interconnected. Chemically, Challenger Deep reveals how Earth cycles elements over long timescales. Carbon, nitrogen, sulfur, and other elements do not simply move through surface ecosystems and return to the atmosphere. Significant portions are transported into the deep ocean and buried in sediments, sometimes for millions of years. Trenches act as funnels in this process. Organic material that sinks from the surface accumulates preferentially in these deep basins. Over time, this contributes to long-term carbon sequestration. The deep ocean is not just a passive reservoir, it actively shapes the planet's carbon balance. This has implications for understanding climate. Surface climate models that ignore deep-sea carbon storage are incomplete. Challenger Deep shows that Earth's climate system extends far beyond the atmosphere and upper ocean. Changes at the surface propagate downwards slowly but persistently, and the deep ocean responds on timescales that exceed human lifespans. Biologically, the trench forces a re-evaluation of habitability. Life persists under conditions once considered incompatible with complex organisms. This challenges surface-centric definitions of what Earth is capable of supporting. It suggests that life is not an anomaly confined to narrow environmental bands, but a persistent phenomenon that adapts to a wide range of conditions. This has implications for understanding Earth's biosphere as a whole. Most life by volume exist in environments that are dark, cold, and under pressure. Surface ecosystems, though visually dominant, represent a minority of Earth's living space. Challenger Deep also teaches restraint. It demonstrates that not all parts of the planet are equally accessible or equally interpretable. Some environments resist observation not because of lack of effort, but because of fundamental constraints imposed by physics and chemistry. This forces scientists to confront the limits of measurement. Data from extreme environments is sparse, indirect, and often ambiguous. Interpretation requires caution. Models must incorporate uncertainty rather than eliminate it. This lesson runs counter to narratives of total understanding. Challenger Deep does not suggest that Earth can be fully mapped, catalogued, and explained with enough technology. It suggests that some aspects of the planet will always be understood probabilistically rather than definitively. The trench also reveals how slow Earth can be. Many processes operating there unfold over thousands or millions of years. Sediment compaction, chemical diffusion, evolutionary adaptation, and tectonic movement proceed at rates that feel static on human timescales. Yet over geological time, these slow processes shape continents, oceans, and life itself. This challenges human expectations of change. At the surface, change is often rapid and visible. In the deep ocean, change is subtle and cumulative. Challenger. Deep teaches patience, both scientifically and philosophically. Another lesson is humility. The deepest place on Earth has been visited only a handful of times by humans. Vast areas remain unobserved. Even with modern technology, knowledge advances incrementally. Each new dataset answers limited questions while revealing additional gaps. This humility influences how Earth science is practiced. It encourages interdisciplinary approaches, long-term monitoring, and conservative interpretation. It discourages overconfidence. Challenger Deep also highlights vulnerability. Despite its extreme conditions, the deep ocean is not immune to surface influence. Human-made pollutants have reached the trench. Chemical signatures of industrial activity appear even here. This demonstrates how deeply human activity has penetrated Earth's systems. The lesson is sobering. No part of the planet is truly isolated. Actions taken at the surface propagate downward, slowly but inevitably. Understanding Earth requires acknowledging this connectivity and responsibility. There is also a lesson about perspective. Challenger Deep exists out of sight, yet it plays a role in shaping the planet people depend on. Many of Earth's most important processes occur beyond direct human experience. This disconnect can foster complacency. The trench challenges that by making the invisible consequential. From a methodological standpoint, studying Challenger Deep teaches scientists how to work with incomplete information. It reinforces the importance of indirect measurement, modelling, and inference. These skills are transferable to other fields, from climate science to planetary exploration. In this sense, Challenger Deep functions as a training ground for understanding complexity under constraint. It forces researchers to operate without full access, without repeatability, and without certainty. This lesson extends beyond science. It has philosophical implications. It suggests that Earth is not a machine that can be fully disassembled and understood piece by piece. It is a dynamic system with emergent properties that arise from interactions across scales. Challenger Deep teaches that depth matters, not just physically, but conceptually. It adds dimension to understanding. Without accounting for what lies beneath, explanations remain shallow. As scientists integrate insights from the trench into broader frameworks, Earth begins to look less like a surface world with hidden depths, and more like a deep world with a thin, active skin. This inversion changes priorities. It emphasizes long-term processes over immediate outcomes. It highlights stability and persistence alongside change. The unsettling part is that these lessons do not come with closure. They complicate understanding rather than simplifying it. They expand the scope of what must be considered. Challenger Deep does not provide a neat summary of Earth's behaviour. It provides a reminder that Earth operates across ranges of scale and condition that challenge human perception. It reveals that the planet's most extreme environments are not marginal, but integral. And once Earth is understood in this way, another realization follows naturally. If the deepest place on the planet reshapes how scientists understand Earth, then it must also reshape how they think about life beyond Earth. Because environments once dismissed as uninhabitable may, under the right conditions, be far more viable than surface intuition suggests. Studying the deep ocean forces a fundamental shift in how life is defined, understood, and expected to behave. For much of scientific history, life was framed around a narrow set of conditions that mirrored human experience. light was assumed to be essential. Moderate temperatures were treated as a requirement. Pressure was something to be avoided, not accommodated. These assumptions were not arbitrary. They were based on what was visible, accessible, and abundant at the surface. The deep ocean dismantles that framework piece by piece. At depths approaching Challenger Deep, life persists in conditions that invert nearly every surface expectation. There is no sunlight. Temperatures remain near freezing. Pressure exceeds anything humans encounter naturally. Energy is scarce and irregular. Yet biology continues, not barely, but with enough consistency to form ecosystems, however sparse and slow-moving they may be. This forces a redefinition of necessity. Light, once considered fundamental, becomes optional. Warmth becomes incidental. Abundance becomes irrelevant. What matters instead are stability, time, and the ability to adapt chemistry to constraint. One of the most important conceptual shifts comes from realizing that life does not need to be fast to be successful. Surface ecosystems reward speed, rapid growth, quick reproduction, and constant competition shape visible life. In the deep ocean, these traits become liabilities. Energy is too scarce to support rapid turnover. Instead, life favors efficiency, patience, and longevity. Organisms here may take years to grow incrementally. Reproduction may be rare and episodic. Metabolism is tuned toward conservation rather than expansion. These strategies are not signs of weakness. They are optimal responses to conditions that have remained stable for millions of years. This reframes evolution itself. At the surface, environmental variability drives constant adaptation. Seasons change, climates shift, disturbances occur frequently. In the deep ocean, variability is minimal, darkness is permanent, pressure is constant, temperature barely fluctuates. Under these conditions, evolution favors specialization rather than flexibility. Studying these systems highlights that evolution is not inherently driven toward complexity or speed. It is driven toward fit. In stable, extreme environments, fit looks very different than it does in dynamic, energy-rich ones. Another shift comes from understanding that life does not require a direct connection to the sun. At the surface, nearly all ecosystems are ultimately solar-powered. Photosynthesis forms the base of food webs. In the deep ocean, that connection is indirect at best and absent at worst. Energy arrives as chemical compounds, sinking organic matter, or slow geochemical processes. This reveals that life's relationship to energy is more versatile than previously assumed. Biological systems can organize around chemical gradients instead of light gradients. They can persist on low, steady inputs rather than abundant, fluctuating ones. This realization alters how scientists think about the boundaries of life. It expands the range of environments considered potentially habitable. Places once dismissed as too dark, too cold, or too pressurized must be reconsidered. Life is no longer confined to narrow bands around stars or within temperate zones. Importantly, this shift is grounded in observation, not speculation. The deep ocean provides empirical evidence that life adapts to extremes without requiring exceptional circumstances. It does so quietly, persistently, and without spectacle. Another way deep ocean research changes thinking is by challenging assumptions about resilience. Surface ecosystems often recover quickly from disturbance. Growth is rapid. Populations rebound. This fosters the impression that life is robust and self-correcting. In the deep ocean, recovery is slow. Disturbance can erase communities that took centuries to establish. Sediment disruption, chemical imbalance, or physical damage may persist for generations. This reveals a different kind of vulnerability, one tied not to fragility, but to time. Life here is resilient in the sense that it endures harsh conditions, but it is fragile in the sense that it cannot adapt quickly to sudden change. This distinction matters. It forces a more nuanced understanding of what resilience actually means. Studying the deep ocean also highlights the role of constraints in shaping biological innovation. At extreme depth, options are limited. Structures must withstand pressure. Biochemistry must function under compression. Energy must be conserved relentlessly. These constraints channel evolution along narrow paths. The result is not stagnation, but divergence. Life evolves solutions that look strange by surface standards, but are perfectly suited to the environment. Proteins fold differently. Membranes are composed differently. Entire metabolic pathways shift. These differences are not cosmetic. They represent alternative ways of solving the same fundamental problems, maintaining structure, extracting energy, reproducing, and persisting. Seeing these solutions in action broadens the conceptual toolkit scientists use to think about biology as a whole. It also undermines anthropocentrism. Human comfort zones are revealed to be poor guides for biological possibility. The fact that humans cannot tolerate deep ocean conditions says little about life's ability to do so. This realization feeds back into surface biology. It encourages researchers to revisit assumptions about marginal environments on land, such as deserts, polar regions, and subsurface ecosystems. If life thrives under pressure and darkness, then many environments previously considered secondary may be more central than assumed. Deep ocean study also changes how scientists think about time. Biological processes at depth operate slowly, growth rates are low, turnover is minimal, evolution proceeds incrementally. This long view contrasts sharply with the fast cycles observed at the surface. Adopting this perspective encourages patience. It emphasizes the importance of long-term observation. Short-term studies may miss meaningful trends entirely. Understanding deep-sea life requires commitment across decades, not seasons. This temporal shift has practical consequences. Funding structures, research planning, and publication expectations are often misaligned with the timescales required to study deep ecosystems effectively. Recognizing this mismatch is part of the intellectual adjustment the deep ocean demands. Another important shift concerns interaction. Surface ecosystems are characterized by dense networks of interactions. Predation, competition, and symbiosis are constant. In the deep ocean, interactions are sparse and infrequent. Encounters between organisms may be rare events. This scarcity alters how ecological relationships are structured. Competition is reduced, opportunism increases. Survival depends less on outcompeting neighbours and more on enduring isolation. This challenges models of ecology built on dense interaction networks. Studying these sparse systems forces scientists to consider ecology in a different light. It highlights the role of chance encounters, slow accumulation, and long-term persistence rather than constant interaction. The deep ocean also changes how scientists think about observation itself. Many organisms cannot be studied directly. Sampling alters them. Decompression destroys them. Visual observation is limited. Researchers must infer function from genetics, chemistry, and behaviour captured briefly on camera. This reliance on indirect evidence sharpens methodological rigour. It demands careful interpretation and restraint. Conclusions must remain provisional. Confidence must be earned slowly. These habits influence scientific thinking beyond deep-sea biology. They reinforce the value of uncertainty as a legitimate scientific state. They encourage transparency about limits. They counter the temptation to overinterpret sparse data. There is also a shift in ethical perspective. Recognizing that deep-sea life operates on long timescales and recovers slowly changes how disturbance is viewed. Actions that seem minor by surface standards may have outsized consequences at depth. This awareness feeds into debates about deep-sea mining, waste disposal, and exploration. Studying deep ocean life does not just expand knowledge, it imposes responsibility. The deep ocean also acts as a mirror. It reflects back assumptions that science has made unconsciously, shaped by accessibility rather than universality. By studying life where human presence is minimal, scientists are forced to confront biases rooted in convenience. This confrontation is productive. It leads to broader, more inclusive definitions of life and habitability. It encourages interdisciplinary collaboration. It aligns biology more closely with physics and chemistry. Perhaps the most profound change is philosophical. Studying life in the deep ocean weakens the idea that life is rare or fragile in the cosmic sense. On Earth, life has colonized environments once thought impossible. It has adapted to extremes without collapsing into simplicity. This does not guarantee that life exists elsewhere, but it reshapes probability. It suggests that given time, stability, and energy gradients, life finds ways to persist. This insight feeds directly into astrobiology. Subsurface oceans on icy moons, buried beneath kilometers of ice, share characteristics with Earth's deep ocean: darkness, pressure, chemical energy. Studying Earth's Hadal zones provides a template for thinking about these distant environments grounded in real data. Even without leaving Earth, the deep ocean changes how scientists talk about life's limits. Limits become context-dependent rather than absolute. Boundaries become flexible rather than fixed. The unsettling part is not that life survives in such places. It is that it does so quietly, without drawing attention, without conforming to expectations, and without needing to be seen. This challenges a deeply human assumption that significance must be visible. In the deep ocean, significance accumulates slowly and operates out of sight. As scientists absorb these lessons, the narrative around Challenger Deep shifts. It is no longer just a place of extreme conditions. It becomes a teacher, reshaping foundational ideas about biology, resilience, and possibility. And once life is understood as adaptable beyond surface intuition, another realization follows. If studying the deep ocean changes how scientists think about life itself, then it also forces them to confront where human understanding still ends, and why certain environments continue to inspire not confidence but unease. Exploration is often framed as a story of progress. Each boundary crossed becomes a foothold for the next advance. Maps fill in. Unknowns shrink. Confidence grows. This narrative works reasonably well in environments where access improves steadily with technology. The deepest parts of the ocean refuse to follow that pattern. At depths approaching Challenger Deep, exploration reaches a hard edge that technology does not easily soften. The limits encountered here are not temporary obstacles waiting to be solved. They are constraints imposed by physics, materials, and human physiology. They define not just what is difficult, but what may remain permanently out of reach. The first limit is obvious but profound. Humans cannot exist here without total technological mediation. There is no acclimation period, no gradual adaptation. Without a pressure-resistant shell, the environment is instantly fatal. This creates a categorical separation between observer and environment. Unlike mountains, deserts, or even spacewalks, there is no moment where the human body can engage directly with the surroundings. This separation changes the psychology of exploration. The environment is never touched. It is never felt. It is observed through layers of metal, acrylic, sensors, and screens. Every sensation is filtered. Every impression is mediated. Presence becomes indirect. This distance matters because it limits intuition. Humans rely on sensory feedback to judge risk, scale, and context. At extreme depth, intuition has no data to work with. Pressure is invisible. Distance is abstract. Motion is inferred from instruments. Exploration becomes an exercise in interpretation rather than experience. This creates unease, not fear in the dramatic sense, but a persistent awareness that understanding is provisional. When observation is indirect, confidence must be earned slowly. Mistakes are harder to detect. Assumptions linger longer than they should. Technological limits compound this problem. Materials can only withstand so much pressure before safety margins become impractical. Hull thickness increases weight. Weight increases energy requirements. Energy storage limits mission duration. Every improvement introduces new constraints. As a result, progress is incremental rather than exponential. Each generation of submersible extends capability slightly, not dramatically. Depth limits move by tens or hundreds of meters, not kilometers. The deepest places remain near the edge of what is possible. This plateau unsettles scientists accustomed to rapid advancement in other fields. Computing power grows exponentially. Imaging resolution improves steadily. Communication becomes faster and more reliable. In the deep ocean, improvement is slow, expensive, and uncertain. The environment resists scaling. Sending one vehicle down is difficult. Sending many is exponentially harder. Building networks of instruments at depth faces logistical and financial barriers that do not diminish easily with experience. This resistance feeds a subtle fear, not fear of catastrophe, but fear of stagnation. The concern that certain questions may remain unanswered not because of a lack of curiosity, but because of insurmountable constraints. The unknown below is not shrinking at the expected rate. There is also fear embedded in data gaps. Vast areas of the Hadal zone remain unmapped at high resolution. Many regions have never been visited at all. Biological surveys are sparse. Long-term monitoring is rare. Scientists know that important processes are occurring, but they cannot observe them directly or continuously. This awareness produces unease because it undermines completeness. Models must be built on partial information. Conclusions must be hedged. Confidence intervals remain wide. For researchers trained to seek precision, this persistent uncertainty is uncomfortable. The fear is not that something hostile is waiting in the darkness. It is that complexity exists beyond current capacity to measure it. There is also a historical dimension to this unease. Science carries a legacy of overconfidence. Past generations declared certain environments lifeless, certain processes impossible, certain limits absolute. The deep ocean has repeatedly overturned those declarations. Each surprise erodes certainty. If life exists where it was not expected, if chemistry behaves differently under pressure, if geology operates outside established models, then other assumptions may also be incomplete. This breeds caution. Scientists working in extreme environments tend to be conservative in their claims, aware that unseen variables may still be shaping observations. The fear of the unknown below is therefore not irrational, it is informed. It arises from experience with environments that resist simplification. There is also an ethical dimension. As interest grows in exploiting deep-sea resources, scientists are asked to assess impacts in environments they do not fully understand. Mining proposals, waste disposal plans, and infrastructure projects move faster than deep-sea science can comfortably support. This mismatch creates anxiety. Decisions with long-term consequences may be made based on incomplete knowledge. The deep ocean's slow recovery amplifies the stakes. Mistakes cannot be undone quickly, if at all. The limits of exploration thus intersect with limits of governance. Knowing where science ends and policy begins becomes more difficult when uncertainty dominates. Another source of unease is temporal. Many processes at depth operate on timescales that dwarf human planning horizons. Sediment accumulation, chemical diffusion, and biological adaptation unfold over centuries or longer. Short-term studies may capture noise rather than signal. This temporal mismatch creates blind spots. Changes induced today may not become visible for generations. Accountability becomes diffuse. Responsibility stretches across time. The unknown below is not just spatial, it is temporal. There is also the matter of irreversibility. Some environments, once disturbed, may never return to prior states. Deep-sea ecosystems are shaped by long-term stability, introducing rapid change risks, pushing them beyond thresholds that cannot be crossed back. Scientists understand this intellectually, But working under uncertainty makes quantifying risk difficult. How much disturbance is too much when baseline conditions are not fully known? Where does precaution end and paralysis begin? These questions generate unease because they lack clear answers. The deep ocean also challenges narratives of human mastery. Exploration elsewhere has often reinforced a sense of control. Maps are drawn, routes are established, hazards are mitigated. In Challenger Deep, mastery feels out of reach. Control is temporary and conditional. This challenges cultural expectations. Humans are accustomed to turning unknowns into knowns. The deep ocean resists that impulse. It suggests that some unknowns may persist indefinitely. This persistence is unsettling not because it implies danger, but because it implies limitation. Even language reflects this. Scientists speak of poorly constrained processes, limited data sets, and tentative interpretations. These phrases appear frequently in deep-sea literature. They are markers of humility, but also of unresolved questions. The fear of the unknown below is therefore not emotional in the usual sense. It is intellectual. It is the discomfort of working at the edge of understanding without a clear path forward. This fear shapes behaviour. It encourages collaboration, interdisciplinary research, and cautious interpretation. It discourages sensationalism. It values slow accumulation of evidence over bold claims. In this way, fear becomes productive. It tempers ambition. It aligns exploration with responsibility. The limits of exploration also force a re-evaluation of goals. Instead of seeking complete coverage, scientists focus on representative sampling. Instead of exhaustive mapping, they prioritize key processes. Understanding becomes strategic rather than comprehensive. This is a shift from exploration as conquest to exploration as stewardship. The deep ocean demands this shift. It does not yield easily. It does not reward haste. It requires patience, restraint, and acceptance of uncertainty. As technology advances, some limits will move. Vehicles will become more robust, sensors more sensitive, data transmission more reliable. But the fundamental constraints imposed by pressure, darkness, and distance will remain. The unknown below will not vanish. It will change shape, receding in some areas while expanding in others. This realization reframes fear. It is no longer something to overcome, but something to incorporate. A signal that attention is required, that assumptions should be questioned, that certainty should be provisional. For scientists, this is not a weakness, it is a discipline. And as understanding approaches its current limits, one final perspective emerges naturally. The deepest place on Earth does not simply hide unknowns, it reflects them back, reminding humanity that knowledge is always bounded, and that some environments will remain unsettling, not because they are hostile, but because they reveal how much remains beyond reach. There is a quiet tendency to think of places we cannot see as places that are passive. Out of sight becomes out of motion, out of relevance, out of awareness. This habit works well enough for everyday life, but it fails completely in the case of Challenger Deep. The deepest place on Earth does not sit dormant beneath the surface, waiting to be rediscovered or explained away. It persists as an active presence, not in a conscious sense, but in the way systems persist, influence, and respond over time. When scientists speak about Challenger Deep watching us, they do not mean observation in the human sense. There is no gaze, no awareness, no intent. What they are describing is something more subtle and more unsettling. The trench records, it responds. It integrates changes from above and below, slowly but faithfully. It does not react immediately, but it does not forget either. This idea challenges a deeply ingrained assumption about directionality. Humans are used to thinking of themselves as observers and the environment as observed. Data flows upward, samples are collected, images are reviewed, conclusions are drawn. Challenger. Deep disrupts this one-way relationship. It reminds scientists that observation is reciprocal, even when the observer does not realize it. Every descent leaves traces. Thrusters disturb sediments. Lights alter behavior. Sampling removes material. Instruments remain behind. Even when efforts are made to minimize impact, presence is registered. In an environment that changes slowly, those registrations persist. This persistence is part of what gives the trench its unsettling quality. It is not that the deep ocean reacts violently to intrusion. It is that it absorbs it quietly. Changes are folded into ongoing processes rather than erased. Over time, these additions accumulate. This accumulation extends beyond direct exploration. Pollutants from the surface reach the deepest parts of the ocean through slow but inevitable pathways. Chemical signatures of industrial activity appear in sediments. Microplastics are detected where sunlight has never reached. These findings force an uncomfortable realization. Challenger Deep is not isolated from human activity. It is downstream from it. In this sense, the trench reflects humanity back to itself, not through mirrors or images, but through chemistry, biology, and sediment layers. What is released at the surface eventually becomes part of the deep. Scientists find this troubling not because it implies immediate danger, but because it reveals how thoroughly interconnected Earth's systems are. There is no safe distance, no depth at which influence ceases. The idea that the deepest place on Earth remains untouched is no longer defensible. The trench also watches in another way, through data that does not resolve cleanly. Measurements taken there often resist interpretation. Signals overlap. Patterns emerge slowly. Variability persists. Scientists return to old datasets years later with new tools and discover details that were not visible before. This delayed clarity creates a sense that understanding lags behind reality. The environment continues to operate regardless of whether it is fully understood. Knowledge chases processes that never pause. In this gap between operation and understanding, unease grows. It is not fear of threat, but awareness of limitation. Challenger. Deep continues to do what it does, regardless of whether humans can model it accurately or explain it convincingly. There is also something psychologically unsettling about permanence without visibility. Surface environments change in ways people can see. Forests grow or burn. Ice retreats. Cities expand. In the deep ocean, change is invisible but no less real. Sediments shift. Chemistry evolves. Biological communities adapt or disappear. This invisibility challenges accountability. It is easier to care for what can be seen, harder to protect what exists beyond perception. Challenger. Deep forces scientists to argue for stewardship without spectacle. The trench also watches through its role in long-term Earth processes. It participates in carbon storage, nutrient cycling, and tectonic recycling. These processes operate over timescales that exceed human planning horizons. Decisions made today may not show consequences for generations. This temporal disconnect is unsettling because it weakens feedback. Without immediate consequences, restraint becomes a matter of principle rather than reaction. Challenger. Deep reminds scientists that delayed effects are still effects. The idea of being watched also emerges in discussions about data completeness. Despite decades of research, the deepest parts of the ocean remain sparsely sampled. Large areas have never been visited. Many processes are inferred rather than observed. Scientists know that unknowns remain, not as small gaps, but as substantial portions of the picture. This awareness produces a quiet vigilance. Researchers are careful with claims. They frame conclusions narrowly. They acknowledge uncertainty openly. This caution is sometimes misinterpreted as hesitation or lack of progress. In reality, it reflects respect for an environment that has repeatedly defied simplification. Challenger Deep also watches through contrast. It exists as a counterpoint to surface assumptions. Every discovery there that contradicts expectations forces reconsideration elsewhere. Life persists without light. Chemistry behaves differently under pressure. Geology operates beyond familiar models. These contradictions ripple outward. They affect how scientists think about other extreme environments on Earth. They influence how planetary scientists think about subsurface oceans on distant worlds. They reshape definitions of habitability, resilience, and stability. In this way, Challenger Deep watches scientific thought itself. It exerts influence not through presence but through implication. It sits at the edge of understanding and quietly reshapes what understanding looks like. There is also an emotional dimension that scientists rarely articulate openly. Working with an environment that cannot be fully accessed, controlled, or observed produces a subtle tension. It is the tension of responsibility without mastery, of influence without ownership. Scientists are trained to reduce uncertainty. Challenger Deep resists that goal. It requires comfort with partial knowledge. It rewards patience rather than decisiveness. It values humility over certainty. This runs counter to many cultural narratives about exploration. The deep ocean does not offer a climax. There is no final map, no complete inventory, no definitive explanation. There is only continued engagement. This lack of closure is what gives the trench its enduring presence. It does not fade into the background once discovered. It remains relevant because it remains unresolved. The idea that Challenger Deep watches us also reflects how it shapes behaviour. Researchers plan cautiously. Engineers overbuild. Policymakers debate impacts with incomplete data. The environment influences decisions even when it is not directly involved. It exerts pressure, not physically on humans, but conceptually. It narrows acceptable risk. It elevates ethical considerations. It complicates economic calculations. In this sense, the trench is not passive. It constrains choices. There is something instructive in this constraint. It suggests that some environments are not meant to be dominated or fully integrated into human systems. They demand different relationships, ones based on observation rather than extraction, understanding rather than control. Challenger Deep embodies this lesson more clearly than most places. Its inaccessibility enforces distance. Its fragility encourages restraint. Its complexity resists simplification. This does not mean it should be ignored. On the contrary, its influence on global systems makes it essential to understand. But understanding here does not mean possession. It means alignment. Scientists working in this field often describe a shift over time. Early work emphasized reaching the bottom, measuring the deepest point, proving capability. Later work emphasizes processes, connections, and long-term patterns. The focus moves away from the trench as an endpoint and toward the trench as a participant. This shift mirrors a broader change in how Earth systems science is practiced. Emphasis moves from isolated features to networks, from static descriptions to dynamic interactions. Challenger Deep fits naturally into this framework. The idea of being watched also emerges when considering future actions. Proposals for deep-sea mining, waste disposal, or expanded exploration inevitably intersect with what is not yet known. Decisions are made under observation, not by the trench but by the uncertainty it represents. That uncertainty functions like scrutiny. It forces justification. It slows momentum. It demands evidence. In a world accustomed to accelerating change, this slowing effect is noticeable. It frustrates some. It reassures others. It signals that not all systems respond well to speed. Challenger Deep continues to exist beyond schedules, budgets, and attention cycles. It does not require engagement to persist. It does not reward neglect with simplicity. In that sense, it watches by remaining itself. The darkness does not conceal emptiness. It conceals activity that unfolds beyond immediate perception. The trench is not waiting to be discovered again. It is already integrated into Earth's functioning. Scientists know this, even when they cannot articulate it fully. It shapes how they approach the unknown. It tempers ambition with caution. It replaces conquest with curiosity. The unsettling part is not that the deepest place on Earth is mysterious. Mystery is expected. The unsettling part is that it remains consequential, regardless of whether it is understood. Challenger. Deep does not need to reveal itself to matter. It does not need to be seen to act. It does not need to be named to persist. It remains beneath familiar waters, shaped by forces older than humanity, operating on timescales longer than memory, integrating signals from above and below, and as long as it continues to do so, it will remain present in scientific thought, not as a solved problem, but as a reminder that some parts of the world do not yield to certainty, and that understanding, when it comes, arrives slowly, shaped by patience rather than revelation.